Good evening, my dear warriors. Welcome aboard to the Roar series. And today we are finishing off capacitors and current electricity by doing all the concepts related to equivalent resistance and equivalent capacitance. You will see most of the things are related. In fact, we are also going to extend it to equivalent cells and equivalent batteries. So that will also include Kirchhoff's voltage law, Kirchhoff's current law, and some circuit related problems. Okay, so it's going to be a very intense lecture. And since a lot of things are related, you will study that in a much more efficient manner. Okay, so that's the reason we have done this. Lecture 1 of current electricity done. Lecture 1 of capacitors done. So this is the lecture 2 of both of these because we have a lot of related stuff. All the warrior Pandus whistle Podo quickly. Hello Shiva, hello Adiksha, Janvi. Yes, Janvi, I know the classes happened after a time because I was in Delhi and I hope you know that. Yes, so now we are back. Hopefully, you guys are going to be very, very regular. I want to see that attendance in a very regular manner because, anyways, all the classes are happening, be it chemistry, be it your mathematics, be it your physics. So be regular, be sincere, everything will continue. All right. If I don't see that seriousness, then we'll have to take a call. Okay, chalo, let's begin. And this is your Captain Shreyas from your Vedantu guys, and being teaching for more than 13 years now, sending kids just like you into the top-notch dream government colleges or whatever private colleges you are looking for. Okay, so let's begin and mark your attendance quickly. Yes, do that right now, even if you're watching it recorded. And if you have not yet subscribed to the channel, do that as well, or else you'll miss out on so much of content. Now, the main basis of finding equivalent circuits or equivalent capacitance or equivalent batteries or equivalent resistors comes through Kirchhoff's rules. These Kirchhoff rules are also called as circuit laws. These Kirchhoff rules, they are also called as the circuit laws. They are basically helpful to find current, voltage, resistance, etc. And it is applicable every time. It is applicable. It is applicable all the times. But keep in mind one simple thing, and that is it can be lengthy. It can be lengthy way of solving the question at times. So you will see more than often we try to solve the questions without using Kirchhoff's rules as much as possible. But wherever there is no other option, we have to use the Kirchhoff's rules so as to simplify the questions. Is that right, my dear warriors? Till this point, is that absolutely clear? Very good. Keep it up, and yes, join in. Make sure others too are joined in into the session. These rules are based on basically two principles. We'll talk about it. One rule is at a junction, other rule is for a loop. So understand the difference between a junction and a loop. So whenever you have a point and there are multiple wires connecting to that particular point is called as a junction. Like you have a railway junction. Lot of railway tracks meet at a particular station. That is what you call as a junction. The second thing that you have is basically called as a loop, where you might have some complex circuit. Let's say, for example, something like this. Okay. And this is a complex, for example, circuit in this particular manner. A loop, a loop is where you start at a point, you start at a point and you come back at the same point again. So this is basically a loop. A loop is a part of the circuit where you start and come back at the same point. So these are the two things which you will need to study, the two important rules of Kirchhoff's law. So first one is also called as the junction law because it is applicable at a node or a junction. Node means a point of connection. Junction means a point of connection of multiple wires. And this particular law, which states that whatever current enters inside a node will also be the current which will exit out. is a simple fact based on the law of conservation of charge. Imagine these were like roads and the current was like cars. Whatever cars which are going through these roads enter this particular traffic signal, they will eventually leave out. So no car assuming is destroyed, nor there is a car manufacturing company over here. So the same thing can be applicable for charges. So whatever charges enter in should exit out, per unit time. That is basically Kirchhoff's junction rule or Kirchhoff's current law or Kirchhoff's law for a node. So this law is based on, so I can say it is based on the law of conservation of charge, on the law of the conservation of the charge. And it says that the total current which goes inside will be the total current which basically goes outside. In this particular example, if you take it, whatever current is entering in is basically I1 plus I2. Whatever current is exiting out is I3 and I4. So this will be equal to I3 plus I4, as simple as that. Okay, this is called as a Kirchhoff's current law. There could be simple examples based out of it. Like for example, I've seen a question something like this, which has, lot of wires here and there, and you have things like this, and they can give you things like, okay, this is 5 amperes. Okay, listen, this is 2 amperes. Listen, um, this is 1 ampere. Let's say this is 6 ampere. Let's say this is 2 ampere. Let's say this is 3 amperes. Okay, and the question will be, how much is the current in this particular branch? How much is the current in this particular branch? How are we going to do this kind of a question? Okay, all you need to do is apply the junction rule at every single node or the joint that you see in this entire circuit. Yep. Yes, Adiksha, correct. So let's see how we solve this. Sir, I'm following your Nurture and Pathfinder series, sir. Is it it's just amazing. Currently, I'm doing fluid mechanics. Amazing, Jan. Amazing. I mean, you can continue using my old series. That is perfectly good content. In fact, whatever I'm doing here is an updated content with newer variety of questions or new questions. That's all I'm doing. Okay. So please follow whichever series you like. But of course, live is at any day is better because you will stay motivated and you will see some newer questions as well. So over this junction, you can see that 5 is coming in, 2 is also coming in. So 100% 5 plus 2, which will make it how much? It is going to be 7 amperes. Now over here, at this particular junction, 6 is entering in, 1 is coming out. So the remaining 5 amperes should come over here. Correct? This 5 has come from 6 minus 1, which is equal to 5 amperes. So 5 amperes is going here because out of 6, 1 goes here. So remaining 5 should go over here. In this case, the 3 amperes is entering in this junction. 2 is going here. Out of 3, 2 went. So how much will go over here? So 3 minus 2, which is basically 1 ampere. Now that 1 ampere will also obviously come over here. And this 5 ampere will also come over here. And together at this particular junction, what you will have is 1 plus 5, which is basically 6 amperes. So 6 amperes is entering here. From here, 7 amperes is entering. So what will come out? So 6 from here, 7 from here, guys. What will be coming out over here is 13 amperes. So the answer for this question is 13 amperes. How many of you got this, my dear warriors? Quickly let me know in the chat box. If you guys got it, proud of all of you. Hello, Boltzmann. Yes. Welcome aboard. Hello, Harborine. Yes. Very good. Very good. So this is how you use Kirchhoff's current law. Now let's talk about Kirchhoff's voltage law. This particular law, like I said, is applicable for a loop. And what is the meaning of a loop? Where you start from a point and you come back to the same point by moving across different devices, capacitors, batteries, wires, switches, whatever it is. You should come back to the same place. So imagine there is a complex circuit. You start from a point and come back to the same point. Every device that you encounter will either increase the voltage or will decrease the voltage or will not change anything at all. So as you travel across a loop, voltage increases, increases, decreases, increases, decreases, decreases, increases, stays same, increases, decreases. But finally, when you come back to the same point, you have come back to the same voltage because you have come back. So that means the net voltage difference should be zero. So whatever increases were there, exactly that many decreases were there. So that you will see that the net voltage drop will be zero because you have come back to the same point, meaning same potential. So this is based on the law of conservation of energy. It's like gravitational energy. You take a mass, you take it up, take it down, take it up, take it up, take it down, take it up, take it down, take it down, whatever. You can bring it back to the same point. Energy will be conserved. The potential energy will be retained back. So there is no net change of potential energy. Same way, there is no net change of potential. Hence, the net potential drop is going to be zero. So this is completely based on law of conservation, law of conservation of basically energy, law of conservation of energy. Keep that in mind. And I can then say that the net voltage drop across different devices, whatever devices you encounter, across a loop, across a complete loop, should be basically zero. Should be basically zero. This is your basic Kirchhoff's voltage law, but you can also slightly modify it at certain places. Instead of going across a complete loop, sometimes people might go from one point to another point without completing the loop. Then also you can do one thing. You start from one point, let's say initial point, plus you encounter some devices which have some voltage differences. Though you measure how much that voltage differences are. Finally, what you get is the potential at our final location. So you start at a point, maybe the voltage is 2 volts. You increase, decrease, increase, decrease, increase, whatever. So finally, when you add all those voltage drops to the initial voltage, what you get is the voltage at the final point. Now, if think about it, the final and the initial locations are the same. What will happen? Both of them will cancel from RHS and LHS. That's why across a loop, you will get the net voltage drop as zero. Did you guys understand it? Here, in this case, the initial and final points could be different. I started from here and ended here. Initial and final is different. So, I will get two different values on the LHS and RHS. But imagine a situation where my initial and final location is same. So what will happen? This and this will cancel. So what will this become? This will become basically zero. Is that understood now, my dear lions? Clear? Give me a thumbs up. Everybody with me on this? Bullsman, I know the many students in BITS and it's doing pretty well. In fact, they have very good clubs for startups and in general for entrepreneurship. Thank you, Bullsman. Love you too, bacha. Yep. Okay. Sir, within this live electrostatic potential and capacitance and current electricity will be over. Yes, Mr. IIT, but let me remind you that we have done lecture 1 before this. So in case you have not watched that lecture 1, please do that. It is there over here. Just check out this playlist on the home page, right? You can see it right over here. Gauss law, electrostatic field, it's done. Then ray optics, we done. Current electricity lecture 1 is done. Capacitors lecture 1 is done. Today we are doing this. Okay, so if you have not yet watched these two classes, please do that because there are additional concepts over here. Cool. All right. So this is something which you should know. Now the main problem is this voltage difference which is there. What is the sign for it and what's the value for it? Okay, so let's talk about that. So what is the value of it and what's the sign of it? So it's very straightforward. Whenever you encounter any device, it could be in our JEE syllabus, either capacitor, resistor or a battery. So say for example, it is a resistor that you are encountering, okay, and let's say the current in it is basically I, or it could be a capacitor, or it could be basically a capacitor of capacitance C. Maybe this is having a plus Q charge and this is having minus Q charge, oppositely charged, right? Or it could be basically a battery, maybe something like this. This is the positive terminal, this is the negative terminal having EMF E. So whenever you encounter a device, either the voltage can drop or it can increase. Now, in the case of battery, say for example, if one happens to go through this battery, from this point to this point, you are going from negative to positive terminal. So there will be a jump of plus E. So this delta V that you are talking about, that change in the voltage, it will be incremented. That value will be basically plus E. Makes sense. I'm traveling in a circuit and I encounter this battery. If this battery has 7 volts EMF, I will jump the voltage by 7 volts across the battery. Obviously, the reverse will also hold true. If I'm traveling in a circuit and I encounter this battery, but I'm traveling like this, I'm going from positive to negative terminal. So the jump will be minus E, or the change will be negative. I hope that makes sense. Very good. Similarly, for this particular capacitor, what you will notice is if anybody is going in a circuit and then you encounter this capacitor going from negative to the positive terminal, obviously there should be a jump. Remember, Q is C into V, so V is Q by C. So the voltage jump will be nothing but Q by C, and that will be obviously positive. But if somebody encounters this capacitor going like this, right? If you're going like this, then what will happen? It will be a jump downwards. It will be negative Q by C. Is that making sense? Because I'm going from higher to lower voltage. Please mind it that the direction of the current inside the battery does not have any role to play in this particular scenario. So current does not matter. What matters is the terminals. Here, which plate has been assumed to be positive charge or negative charge matters. What happens in case of the resistor? Here, the direction of the current matters. You will see that current in a resistor always goes from high to low voltage. So this is higher voltage, this is lower voltage. So if I go from here to here, that means I'm going from low voltage to high voltage. So hence the jump should be plus IR using Ohm's law. Current into resistance is voltage. So that is what I'll get. But if I'm going like this, then it will be negative IR. So this is basically the simple sign convention. This is the simple sign convention which you should be aware of. So say for example, my dear warriors, okay, let's take a random circuit with some elements in it. Let's say there is a resistor here, and let's say then there is a capacitor here. Then there is maybe some kind of a battery here. Okay, then there is a resistor here, some terminal here, then maybe some battery over here. Okay, battery over here, some resistor here, like this. Okay, and maybe something like this, another capacitor over here, another capacitor over here, okay, something like this, and maybe a resistor here like this, and maybe a battery over here like this. Okay, so this is a random circuit which I have taken. Let's say this is R1, let's say this is C1, let's say this is E1, this is R2, this is E2, this is R3, this is E3, then this is R4, then C1 is done. Okay, let's say this is C2. Okay, let's say this is positive, negative. All right, and let's say this is negative, this is positive terminal, something like that. And some currents also need to be assumed. Let's say this is I1 over here. Maybe this part I don't need the current. Let's say current over here is I2. Okay, let's say the current over here is, let's say, I3, and let's say the current over here is, let's say, I4. Okay, I've just taken some random circuit, guys, and I'm trying to figure out how I will apply Kirchhoff's voltage law based on this sign convention. Let's start. Let's decide a path. Let's decide a particular path and follow that path. Which path do we want to take? Let's say I want to start from here. I want to go like this. I want to go like this. I want to go like this. I want to come back over here. I want to come back over here. I hope you are able to see that particular path. Let's apply Kirchhoff's current law, sorry, Kirchhoff's voltage law, and see what do we get. Let's start. Starting from here. Okay. Here I'm encountering a resistor. If I go in the direction of current, what happens? If I go in the direction of the current, I am going to go from high voltage to low voltage. So it is negative IR. So the first thing that I will get is basically negative IR. As simple as that. So what I get over here is negative IR. Okay. Then I'm going through a capacitor. I'm going from the positive side to the negative side. That means high to low. That means again there is a drop. And that's why I'll put a minus sign and it will be Q by C. Q by C. Perfect. When I encounter a battery, I'm going from negative to positive. If I'm going from the negative to positive, that means I'm taking a jump. So hence it will be plus E1. It will be plus E1. Sorry, this was Q1 and C1. My bad. This is Q1 and C1. Yeah. Now from here, I'm going through this resistor. I'm going against the direction of the current. What happens when I go against the direction of the current? There is a jump. There is a jump, right? Because current always goes from high to low. So if I'm going from low to high, it's a jump. So it will be positive. So it will be plus I to R2. It will be plus I to R2. Till this point, is that clear? I hope this is clear. Everyone? Awesome. Next, from this point to this point, I'm going through a battery from positive to the negative. Positive to negative, that means there is a degradation. So negative. So negative E2 because I'm going from high to low. Now, here, what is happening through this resistor R3, the current is going like this. But listen, I am traveling against the direction of the current. Current goes from high to low. I will go from low to high. Low to high. That means it's a increase. So it should be positive. So it will be plus I3 R3. It will be plus I3 R3 because I'm going from low to high. Going against the current, it is a jump. Going with the current, I will go down with the voltage. I then encounter this battery. I'm going from positive to negative, so it should be a degradation. So minus E3, minus E3. Then I encounter this resistor. I'm again going against the direction of the current, so it should be a jump. So it should be plus I4 R4. It should be plus I4 R4 because I'm going against the current. And finally, this capacitor, this is negative to positive, so it's a jump. So it should be plus Q2 by C2. And finally, I come back to the same point. Hence, the final answer should be a big fat 0. That's how it is. Is that clear, my dear warriors? Wow. Dharnishwaran took that effort to put it down. Very good. Hello, Nandini BR. NN ideas, the syllabus, I think most of it should be done by October, right? Yeah, because I want to start off with revision. But see, it depends again on you. If your guys are very punctual and serious, then we will put in our 100% to finish it as early as possible. But if you become irregular, no comments, no likes, no shares, because I can see all the data, then we will also not get that motivation. So make sure you are watching, you are sharing, you are involving other people, you are commenting, you are liking everything. I want that engagement because we are doing this all for free on YouTube for all of you. Remember that. It is for you we are doing it, not for me. For you guys, remember. Okay, this is one way. Now, remember, I also told you, you can also use this kind of thing where you start from a point and end at another point. Then what you need to do? Say for example, say for example, uh, let's say I maybe, I don't know, maybe I start at this point and I end over here. I start at this point and end over here. And let's say this particular point, I call it as A. This particular point, I call it as B. So in order to apply the Kirchhoff's law between two random points, which is not a loop, what you need to do? You're starting from A. So start off with initial voltage, that means potential at point A, plus write down all the voltages that you get on the way. In this case, you are getting this resistor and I'm going in the direction of the current. In the direction of the current in a resistor, the voltage will drop. So negative. So minus. So instead of plus, that will be minus I3 R3. That's the first thing that I encounter. Then I encounter a battery from negative to positive. I'm going like this. So there will be a jump, which means plus E2. Then I encounter another resistor. Again, I'm going in the direction of the current. So in the direction of the current, it drops. So minus I2 R2, minus R2, I2 R2. Here, going from positive to negative, so there will be a degradation, there will be a downgrade. So it will be minus E1. Then in this capacitor, I'm going from negative to positive. So it's a jump. It's an upgrade. So plus Q1 by C1. And finally, I reach at point B. So this will be equal to potential at point B. So if I know VA, I can find VB. If I know VB, I can find VA. And if you want, you can also find VA minus VB also. So if you want, you can also do this. Keep all these people over here. Like, therefore, I can say minus I3 R3 plus E2 minus I2 R2 minus E1 plus Q1 by C1 will be VB minus VA. What is this VB minus VA? It is nothing but the potential difference between points A and B. Between the points A and B, this is the voltage difference. So this is how you can use this law when it is not across the loop. Initial voltage plus all the voltage differences is equal to final voltage. This is exactly what we have used over here. Initial voltage plus all the voltage differences is equal to the final voltage. This is a more generic one. This is a more specific one when you take a loop. Is this clear, everyone? Understood? Shall we go ahead? Let me know quickly in the chat box. Let me know quickly in the chat box. Okay. Now, sometimes what people do is whenever you have circuits, you can also do one more smart thing. That is, imagine there is something over here, something over here. Okay. And I don't know, battery, some resistor. Okay. Something and all you can keep. Okay. Let's say this is I4, this is R4. Let's say this is I1, this is R1, this is positive, this is negative, this is C1, this is E1, this is, let's say, this is R1, this is I2, this is R2. Okay, some random things I have taken over here. Okay, and let's say, for example, they tell you this is having a voltage of V1. Sometimes you mark the potentials. This is having voltage V2. This is having voltage V3. This is having voltage V4. Okay. They tell you voltages of some points, or maybe in a problem, you see that by marking the voltages, it might become a little bit easier problem. This is called as marking potentials. This is called as potential method, where you mark the potentials either known or unknown and then try to solve the problem. So if these are the assumed or given potentials, and you can see there is a wire here, this point and this point, both of them, this point and this point, both of them have the same voltage. I can call it X. I can call it X voltage because they are connected by a wire. They are connected by a wire. You can just treat this like one common thing over here. In fact, you can join both of them together and forget the two x's and think of this like a node. Think of this like a node where there is I2 entering in, I4 exiting out. Maybe there is some current which will go through this as well. Okay, maybe there is some current which will go through this as well. Maybe I can call it I3, right? And maybe there is some current which will go through this. Maybe this is basically I4, something like that. So I can do all these things. I can do all these things. Okay. I can assume these currents. You can keep as many resistors as you want here and there. And then what you can say is that whatever current is entering in is also the current which is exiting out. Whatever current is entering in is also the current which is exiting out. So wait a minute, let me call this as I1 over here. Yeah. So what is the current which is entering in? Let's say I3 is entering in, I2 is entering in, that's it. So I2 is entering in, I3 is also entering in. Who is exiting out? I4 and I1. I4 and I1. So I1 plus I4. Just write the Kirchhoff's current law equation. That's it. Now think what is I2, I3, I1, I4 individual. What is I1? I1 is basically the current through this part, and this current will be voltage by the resistance. Current is basically voltage by the resistance. Similarly, this current will be voltage divided by this resistance. Current will be voltage divided by this resistance here. This current will be voltage by resistance here. If it can't be written down in terms of resistance, I will write it in terms of something else also, but that is okay. So you can now substitute each of these currents. Say for example, I4. What is this current I4? It is voltage by that resistance. So I can write I4 as voltage difference, which is X minus V3 divided by resistance, which is basically R4. Using Ohm's law, current is voltage by resistance, but that voltage is actually voltage difference. So X minus V3 by R4. That's what you can do it. Yes. Similarly, if I want to, let's say, for example, write down the value of I2, what is I2 going to be? I2 is voltage by resistance. So what is that voltage? Think about it. Is it X minus V1 or V1 minus X? Always high minus low. Current goes from high to low. So it will be nothing but V1 minus X divided by the resistance, which is basically R2. So that is what I2 would be. V1 minus X divided by resistance. Now, what about this particular capacitance? What can you write I3 as? Well, think about it. I3, I can write it as dq by dt, dq by dt in that capacitor number 1. And do not forget, Q is actually CV. Q is actually CV. Yes, so you can also write this as d by dt of, instead of this, you can put it as C into voltage. What is the voltage between these 2 points? V2 minus X. You can put V2 minus X over here. If you want, take capacitance 1 outside. So it will just become C1 into derivative of V2 minus X divided by dt. That is also what you can write I3 as. Is that clear, everyone? With me on this? What about I1, guys? What about I1? Think about it. What will be current I1? Think about it. What will be the current I1? It will be the total voltage drop between this point and this point. It will be the total voltage drop between this point and the resistance. But the unfortunate part is there is a battery also over here. So you can do one simple thing. Remember our KVL which we applied between 2 points? Start from a point and go to another point. You can use that equation as well. Just for this region, start from here, go here. If you start here, the potential is X. What you encounter over here is a battery which goes from positive to negative. So there is a drop. So minus E1. Again, I'm going through a resistor. So there will be a drop. So it will be minus I1 R1. Finally, I reach here. So where the potential is V4. So rearrange this. That's all. I just want I1. Remember that. So take all these people over here or bring V4 over here. So X minus E1 minus V4 is I1 R1. So therefore, I1 will be basically X minus E1 minus V4, the whole thing divided by R1. So that is what this particular I1 will be. So you can substitute all these things. This is called as the method of potentials. What is this called? This is also called as the method of potentials. Method of potentials. Method of potentials, where you use Kirchhoff's law or Kirchhoff's voltage law, but you have marked the potentials and then trying to solve it. That's all. Yes, you can by splitting each node, as we used to solve kinematic problems. What do you mean by splitting the each node? Once you take a node, whatever current is entering in and exiting out, all those things should be used, unless, yeah, you want to consider this node separately, and then solve it for this node and this node separately. You can do that, but it will just make the problem lengthy. When you see there is a wire connecting two junctions, just combine them together and solve it like a single node. Okay, let's take up some questions now on Kirchhoff's laws. And here comes the first question on your screen. Find the currents in the different resistors shown in the following figure. Let's see if you guys can figure this out. Come on, my dear warriors. Sorry. Okay. So in this particular question, maybe we can assume some voltages and then maybe we can do it. It will probably look little easy. I think so, because there are too many branches. So whenever I see too many branches, I prefer using uh, method of potentials. So let's do one thing. I can see that these three batteries negative terminals are connected at the same point. They are connected at the same point. So how about assuming the potential as whatever, you can take it as zero. Any point you can take it as zero reference. Remember, I can mark any point as, zero voltage reference, like potential energy at the ground level, we take it as zero, right? So we can take it as zero, or if you want, you can take it as X also. So let's say X is our reference voltage, and this I have just marked it as 0 volts. 0 volts reference. Somebody might say, sir, for me, this is 0. No issues. Somebody might say, sir, this is 0. No issues. The reason why I took this as 0 is because I can see three negative terminals. So let me start with the negative as my base or my reference. And with respect to that, I will start marking the other voltages. See, if this is 0, I go across the battery. What do you think will be this point's voltage? 0 from negative to positive, it will be a jump. So it will be plus 2 volts. From here to here, it will be also plus 2 volts. From here to here, this will be also plus 2 volts. Everybody fine till this point? Okay. Now these two resistors together, I can just combine them. I can just combine both of them together. I can call it as 4 ohms because they are in series. Can you see that? They are basically in series. Same way, this 8 ohms and 8 ohms are also actually in parallel. If you notice carefully, they are actually in parallel, my dear warriors. So if they are in parallel, their resistance effectively will be how much? It will be basically 4 ohms. It will be basically 4 ohms in parallel. Do you see that? Yep. Where we should locate the reference voltage is completely up to you, your choice. Usually choose a point which is common for multiple batteries or for multiple, you can say, capacitors. If there are 2 3 capacitors, in this case there were no capacitors, or a point which looks convenient to measure with respect. Okay, in this case I saw this was the point because all the three batteries negative terminals were combined together, so that's the reason why I took it. But let me tell you, the answer won't change just because I choose some other point as 0 voltage. Yeah, Usha, like I said, tentatively by September, October. That is the aim. All right. Now, there is one unknown point over here. I don't know that voltage. Maybe I will call it as X volts. Maybe I'll call it as X volts over here. And then I can start seeing some interesting things. In this branch, let's say the current which is going is I1. Then in this branch, let's say the current which is going is, let's say, I2. In this branch, let's say the current which is going is basically I3. That's it. So I1, I2, and here that is basically I3. So this is basically I3. This is basically I1. And in this particular branch, it is basically I2. I hope you are able to see that. So how about using Kirchhoff's current law at that particular junction over here? I1 plus I2 and I3 all are entering in. So I1 plus I2 plus I3, current entering in, current exiting out, nothing. So total sum should be 0. What this means is that one of the currents will be negative. Kind of makes sense. How can only current enter inside? But it's okay. I have just assumed the currents to go in. So one of the currents will automatically come out to be negative. That's okay. Perfectly fine. There is nothing wrong over there. Okay. So what is current I1? Think about it. What will be current I1? So there is a resistor, there is a battery over here, and it will be having a voltage of X minus 0. And there is current I1 over here. So if I had to write down a particular equation over here, if I had to write down a particular, oh, this is 2 volts, this is X volts. So the voltage difference is 2 minus X. Isn't it interesting, guys? Just check this out. The voltage difference is 2 minus X and the resistance is 4 ohms. Current is voltage by resistance, so it will be 2 minus X divided by 4. Current is voltage by resistance. Voltage is 2 minus x, resistance is 4 ohms. Perfect. Look over here, I2. Current is voltage by resistance. Voltage is 2 minus x by resistance. So plus 2 minus x by resistance, which is again 4, plus current number 3. This is 2, this is x. High minus low is the voltage by resistance. Oh my God, again it is 2 minus x divided by 4. That is equal to 0. So this I'm getting 3 times. Everybody with me on this? Everybody with me on this? Awesome. So what will happen? This will just become 3 into 2 minus x. The whole thing divided by 4 is basically a big fat 0. 3 into 2 minus x. The whole thing divided by 4 is 0. So basically 2 minus x is basically going to be a big fat 0 because 3 and 4 can't be 0. So therefore x is basically 2 volts. X is basically 2 volts. Now think about it. If x is coming in to be as 2 volts, guys, what will be current I2, I1 or even I3? Just think about it carefully. What will be any of the currents? Remember, I1, I2, I3, all of them coincidentally came out to be equal. All of them came out to be equal, which was 2 minus x divided by 4. But remember, our itself, x value itself came out as 2. 2 minus 2 is 0. So it will be 0 amperes. So all currents are 0. All currents, all currents are a big fat 0. Let's find out whether we are correct. Yes, it is correct. So this is how you use Kirchhoff's laws. What an interesting question. Turned out to be a big fat 0, right? Let's move to the next question. The reading in the voltmeter is how much? This was asked in JEE 2024. Now you can see there are multiple batteries arranged in different ways. You have to measure the voltage between these 2 points. Forget the voltmeter for now. So what will happen is the current will flow through all these batteries. Forget the voltmeter. It is just to measure the voltage, nothing more. There is current which is going like this, and that is I. So if I apply Kirchhoff's law, starting from here, going like this and coming back over here, when I start from here, I encounter this battery with some internal resistance. So if I'm going from negative to positive, I'm jumping in the voltage. So it will be a jump of plus 5 volts. But at the same time, I'm going through a resistor in the direction of the current. In the direction of current, the voltage drops in a resistor. So there should be negative IR. So minus the current into the resistance, which is basically 0.2. 0.2. V is equal to IR. So I is unknown, R is 0.2. So there is an increase of 5 volts and there is a drop of 0.2 into I. Now the same thing will happen here, 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 here. How many times? 1, 2, 3, 4, 5, 6, 7, 8. So this whole thing you multiply it by 8 times and finally you come back over here and the answer is 0. Is that understood? I've just used which law, guys? I've used Kirchhoff's voltage law. That's it. So what will happen? Into 8 is 0. So therefore, 5 minus 0.2 I is basically 0. Shift it on the other side. So 5 is basically 2 divided by 10 into I, right? So I is nothing but 25 amperes. 5 tens are 50, 50 divided by 2, guys. Yes, so that is just going to be 25 amperes. But that is not the question. The question is not the current. The question is the voltage. So how do I find this voltage? So I want to find the voltage difference between these 2 points. Let's say I call this point as A. Let's say I call this point as B. If I start over here, voltage at A, that is initial, plus negative to positive terminal of the battery, so plus 5, minus current into resistance. Current is 25, resistance is 0.2. I reach over here, that is equal to VB. So take VA on the other side, so it will become VB minus VA. That is actually the voltmeter reading. What is this going to be? 5 minus 25 into 0.2. 25 2s are 50 into point, which means 5. So 5 minus 5 is, so the voltmeter reading is 0 volt. Hence, that is the answer, which is option D. Answer is 0. How many of you got 0? Very good, Dharineshwaran. Isn't it a brilliant, brilliant question? Tell me about it. Yes, loved it. Very nice. Awesome, guys. Awesome. Yeah. Thank you, Jayaditya. Yeah. So we have applied Kirchhoff's law in this part of the circuit. I saw that the current was the same. You take any point and you come back to the same point. And since there were 8 such batteries with internal resistance, E minus IR, 8 times it will come. I got the current. Once I got the current, I will apply Kirchhoff's law between these 2 points because I want to find this voltage. VI, which is VA, plus voltage differences is equal to final voltage, which is VB. So take VA on the other side, VB minus VA is the voltmeter reading. Cool. Let's do the next question on Kirchhoff's law. This is a J advanced question. I hope you will enjoy this. In a balanced condition, the value of the resistance of the 4 arms, don't even have to worry what is balanced condition. Just think, okay, there are some resistors, there are some batteries, and Wheatstone's bridge are shown. The resistance R3 has a temperature coefficient of this much. If the temperature of R3 is increased by 100 degrees Celsius, the voltage developed between S and T will be how much? Okay. Now let me tell you, whenever you have a voltmeter in the circuit, right? Whenever you have a voltmeter in the circuit, just like in the previous question, did we even consider it while solving the problem? No. Why? Because voltmeter has how much resistance? A voltmeter has infinite resistance. It does not hamper anything in the circuit. Pavam fellow silently comes, measures the voltage, that's it. It does not do any changes in the equivalent resistance. Or else if it had some resistance, it will change the whole characteristics of the circuit. Some current will go through it, whole things will change. So it does not affect the circuit, an ideal voltmeter. So that is the reason why you can think of it like a very, very large resistance. So just like we ignored it over there, why not ignore it over here also? So first step is to forget this, because that removes a lot of complications and it gives you clarity in the problem. Okay, just forget this. Just forget that this is even there. Now it looks little bit better, number one. Next, coefficient of thermal resistance is given. Resistance will change when you change the temperature. So let's find out the new resistance, of course. So the new resistance will be the old resistance into 1 plus into delta T. That is the formula. The old resistance of R3 is 3 into 1 plus alpha. Alpha is basically 0.004 into temperature, which is 100. So this will be basically 300 and 1 plus 0.04, so zero point 0.4. That's what it will be. Just check this out. Yes, is that right? Oh, sorry, there were 3 zeros, right? There were 3 zeros over here. 1, 2, 3, and then into 100. So this will be 0.04. So 300 into 1.04 will be 312 ohms. Just check this out. So this is the new resistance, which is R3. New resistance, which is R3. Question is, what is the voltage difference between points S and T? Okay. In order to find the voltage between S and T, I think I need to know the currents in these branches. I need to know the currents in all these branches. So in order to find that current, here is what I will do. Observe carefully. Observe carefully, guys. What I will do. Just consider this part. Just consider this part of the circuit separately, and then consider this part of the circuit separately. Let's, think what is exactly happening in this part separate and that part separate. Why? Because I can see, if you consider, exactly this part of the circuit between points P and Q, forget that. Just forget that, because that has nothing to do with this. Between P and Q, the voltage is 50 volts, correct? Between P and Q, the voltage is 50 volts. Maybe the current is going like this. Let's say I call it as I1. Just consider it as I1. So can I then say over here Vp, because I'm going in the direction of the current, start from here, initial voltage minus IR. IR is basically minus I1. What is this? R1. R1 is basically 60. I then go across this resistor. So minus I1 into what is that resistance? 300. Oh, the new resistance. New resistance is 312 into 312 is equal to VQ. Now is the interesting part, guys. If I put Vp minus VQ, bring that VQ over here, these two gentlemen go on the other side. So it will become I1 into 60 plus 312. What is Vp minus VQ? Just tell me quickly in the chat box. Vp minus VQ, it's the battery's voltage, high minus low, battery's EMF, which is exactly 50 volts. I1, I do not know. 60 plus 312, guys, that's 372. That's 372. Is that right? Everyone with me on this matter? Perfect. Awesome. Now do the same approach, but for this part of the circuit. But for this part of the circuit. Same thing you do. Start off with Vp. You can say this is basically your I2. The current is going like this. So Vp minus I2 R2. R2 is basically 100 minus I2 into 500 is equal to VQ. Now again do Vp minus VQ is equal to, take these two people on the other side. So I2 into 100 plus 500. Vp minus VQ, high minus low, EMF of the battery, which is 50, is equal to I2 into basically 600. I2 into basically 600. Now, once I get I1 and I2, once I've got I1 and I2, I think now I can find out. Gauri, what are you saying? Sir, in the circuit, the same battery is providing voltage difference on both the sides, then its potential on both sides will be same. Yes, exactly. The same battery is providing the voltage on both the sides. So either you can ignore this circuit and think there is this battery connected to this circuit, or this battery connected to this circuit, ignoring this. It's one and the same thing. To find between S and T, to find the voltage difference between S and T, start from here, go like this, go across this circuit like this, go like this, and finally reach over here. Start from S. So Vs, so Vs, I'm going against the current. I'm going against the current. So what will happen? There will be an increase. So plus I1 R1, I1 R1. Here I'm going in the direction of the current. So there will be a drop. So minus I2 R2. Finally, where am I reaching? Point number T. So Vt. So take Vs minus Vt, of course, will be, take this guy on the other side. So I2 R2 minus I1 R1. So what is I2? I think we figured it out over here. So which is 50 by 600. What is resistance number 2? That is basically 100 minus I1 is basically 50 divided by 372. What is R1? R1 is basically 60. That's it. You solve this and just find out the mod value. I'm not interested in the actual value. I'm interested in the mod value. Just find it out, and I think it should come out to be as 0.27 volts. It comes out approximately, not exactly, 0.270 volts. Okay, that is the answer. That is the answer to this particular question. Is that understood how we solved it? The first part was using thermal resistance concept. This 300 won't be 300, it will change to 312. And rest of it was applying Kirchhoff's law multiple number of times. We also have used Kirchhoff's current law. We didn't use as such. Yeah, we just use Kirchhoff's voltage law. Yep. Avanesti, you are very late, but hopefully you will be able to catch up. Yeah. I hope you enjoyed these questions, which are exclusively on Kirchhoff's laws, nothing less, nothing more, purely based on Kirchhoff's laws. Okay, right. So with this, let's move on to the, I think the next combination. I will just quickly do this quick, combination of resistors, combination of capacitors, and combination of batteries. So I think resistors in series you have already done back in 11th standard, but just a quick revision because there will be some interesting things. Whenever resistors are in series, what happens is the current is the same. Keep this in mind. The current is basically the same. Each one of them will have some voltage drop. Each one of them will have some voltage drop, V1, V2, V3, etc. So V1 plus V2 plus like that till Vn is the total voltage drop. Keep that in mind. And each one of these voltage drops, each one of these voltage drops will be like I1 into, sorry, current is the same, right? So current into resistance, current into resistance. So same thing over here. This will be also current into the resistance. That's how each of these voltages will be. And the total voltage, of course, will be current into the effective resistance. So you can see I will get cancelled and the effective resistance will be simply put R1 plus R2 plus R3 like that till Rn. So the total resistance is the sum of individual resistance. In fact, it is more than each of the resistances. This is the basic concept when resistors are in series. But when you have resistors in parallel, then you will see that the total current, of course, will get divided into branches I1, I2, I3 like that. So I1, I2, I3 like that. And what will be same across all of them? What will be same? Instead of voltage, it will be basically, sorry, instead of current, it will be voltage. So it's the voltage which is same across all of them. So the voltage is same for all. Whenever you see two or more devices having the same voltage differences connected across the same ends, that means they are in parallel combination. Yep. So in that case, what gets distributed is the current. So you will see that the original current will be I1 plus I2 like that till IN. And each of these currents, let's say I1 will be current will be voltage by that resistance. So this will be voltage by that resistance. This current will be that voltage, which is again the same, divided by that resistance. This current will be again the total voltage, but by total resistance in parallel. So if you equate V will cancel. So you will see 1 by Rp will be 1 by R1 plus like that till 1 by Rn. This is for equivalent resistances in parallel. Now keep in mind, whenever you have two resistances, for two resistances, what happens is 1 by Rp will become 1 by R1 plus 1 by R2, which is nothing but taking LCM R1, R2, and here you will have R1 plus R2. So taking reciprocal, what you get is Rp is nothing but R1, R2 divided by R1 plus R2. This is only for two resistances. If there are more, then you cannot use this formula. You will be forced to use this reciprocal formula. As simple as that. Now, same thing also applies for when you are combining capacitors. In capacitors, instead of current, you will consider the charge. That's the only big difference, whether it is same or not. And here, whenever you have capacitors in series, what will be same is the charge. So positive, negative, positive, negative, positive, negative. So if this is plus Q, this will be minus Q. This is plus Q, this will be minus Q. This is plus Q, this will be minus Q. What will be different is the voltages V1, V2, V3, and so on and so forth. That's what will be different. Now, why is the charge same? There is a simple theory behind it. I'll tell you why. Imagine there is this capacitor like this. Right now, on them, no charges are there. So 0, 0, 0, 0. Now what happens? You charge it, connect it to a battery. You connect it, let's say for example, to a battery like so over here. So if this battery supplies some positive charge over here, where did this positive charge come from? Because some electrons would have, moved from one place to the other. So you can say there will be a negative charge which will be developed here. So, you can see electrons will probably go from here to here. If one electron goes, one negative charge here, one positive charge here. If two electrons go, then two negative charges here, two positive charges here. Remember, always opposite plates will have opposite charges, same magnitude but opposite sign. So this is plus plus, this will be minus minus. If this is minus minus, this will be plus plus. Can you see again, both the inner plates also have the same magnitude of the charge. So we'll see if you have multiple such capacitors also, the same logic applies and charge should be conserved. That's why in series, you will see same charge gets developed magnitude wise on all the plates. Or basically all capacitors have the same charge. Is that right? Hello, Adila. Yes. Um, can we take one loop and solve it? Dharneshwaran, you mean for the previous one? Yes, you can take that one loop also and solve it for the previous one. But you mean, I think this question, where is it? This particular one. But then the question itself said between S and T. So if you take the complete loop, I mean, you might probably get I1, I2, but to find between these two, I will have to use Vi plus voltage differences is equal to Vf. That formula I will still need. So I can say that the charge is going to be the same, but it is the voltage difference which is going to be different. And each of these voltage is Q by C. So it will be Q by C1. This will be also Q by C2 like that, Q by Cn. The net voltage I can say it is Q by Cs. If you equate it, Q will get cancelled and you will see 1 by Cs is 1 by C1 plus 1 by C2 plus 1 by Cn like that. So the formula is like parallel resistors. It's exactly opposite. That's what you should know. And of course, for two capacitors, Cp will be nothing but C1, C2 divided by C1 plus C2. Only for two capacitors. When you have capacitors in parallel, then whatever charge gets supplied will get distributed. Let's say 3 or 4 charges are there. It will, two might go here, one will go here, one will go here, or it will get distributed. So if this is Q1, if this is having Q2, and if this is having Q3, the charges will get distributed. What will remain the same is the voltage, just like in resistors in parallel. So voltage drop is the same. Voltage drop is the same. And the total charge gets distributed as Q1, Q2, Q3, depending on the number of capacitors. Again, remember, each of these charges will be C into V. Capacitance is different, voltages are same. Q2 will be C2 into V. So Qn will be Cn into V. This will be nothing but C parallel into V. Just like this was done for series, same thing we are doing for parallel. If you equate, you will see voltages will get cancelled and you'll see Cp will be nothing but C1 plus C2 plus Cn. So this is like resistors in series. So capacitor formula and resistor formulas are exactly opposite is what you can see over here. That is something we should be careful about. Right. Yes. Then combination of cells, series and parallel, you should know that also. If you are given multiple cells one after the other in series, like you take a battery, connect it to another battery, connect it to another battery, right? Each battery will have its own EMF. Each battery will also have its own internal resistance. You can combine all these batteries and treat it like one single battery with one new internal resistance as follows. The new equivalent series EMF is E1 plus E2 like that till En, and the new equivalent internal resistance is simply R1 plus R2 plus Rn. But there is a small catch over here. If some of the batteries are not pointed in the same direction, they are connected in the opposite direction, then their EMF contribution will be negative. So that's why, to give the benefit of the doubt, I'll put plus minus sign over here. This plus minus is to accommodate the fact that some batteries may not be in the same direction to support. Imagine somebody is pushing, somebody is pushing, somebody is pushing. All people are pushing in a line. They will help each other's push. But imagine one person is standing opposite. they will contribute negatively. So that's why that minus sign is going to be there only for those batteries which are connected in the wrong manner or in the opposite manner. What about resistance? Should I put plus minus? Put it up in the chat box. What do you think? Yes? C. Oh, sorry. I put. No, this is fine. This is CP only. They are capacitors in parallel, but the formula is like series of resistance. In the previous one, this is CS because these are actual capacitors in series, but the formula is like capacitor resistors in parallel. Okay. Yeah. There is no need of plus minus here because resistors do not change just because the current changes the direction. Whether you pass the current like this or pass the current like this, the resistor will maintain its resistance. Okay. In the previous slide, which slide, Mike? Oh, here. Okay. Thank you. Yeah, this should be CS. My bad. Yes, this is CS. Thank you for pointing it out. Now, what about batteries in parallel? There is one battery beside another battery, beside another battery. All of them are in parallel and their wires are connected, bundled together, and you are taking a common input, common output. Like this battery, multiple batteries could be there. See, for resistors, the formula is the same. So we'll still use 1 by equivalent resistance internal is 1 by internal 1 plus 1 by internal 2 plus 1 by internal n for resistors in parallel, whatever formula you used. All right. So that is the internal equivalent resistance. But for internal equivalent EMF, sorry, for equivalent EMF in parallel, this is the logic. Put a big denominator, a numerator line. Okay. Then put over here 1 by R1, 1 by R2, like that, till basically 1 by Rn. Here also R1, R2 in the denominator, of course, till Rn. But on the top, unlike here you put 1, right? Here you put E1, E2, E3. So E1, E2, E3, En. That's all. That's the only difference. So this is the equivalent EMF in parallel. So all these batteries combined together will behave like one single EMF. Is that right, everyone? There is a catch here also. Here you will have to put plus and minus only in the numerator because I do not know whether all the batteries are pointed in the same direction. If some of the batteries are oppositely connected, then you will have to take into account the negative contribution. That's why only in the numerator we'll put negative sign wherever there is EMF. Resistors do not get changed. That's why it remains as it is. Let's learn how to use these formulas, maybe for simple questions. Say, for example, there are, let's say, 10 cells, each of 2 volts and 4 ohm internal resistance. 3 are connected in a wrong way. Find the expected versus real equivalent EMF and internal resistance. Okay, that's the question. Let's see if we can figure it out. Expected versus real. Now, expected is I have taken 10 batteries, one behind the other. All of them are connected in series. All of them are connected. 10 such cells are there in series. So, the equivalent resistance in series internally will be R1 plus R2 plus R3. So 4 plus 4 plus 4, like that, 10 number of times. So ideally you should get the internal resistance as 40 ohm. Internal resistance as 40 ohm. The equivalent resistance, equivalent EMF should be 2 plus 2 plus 2, like that, 10 number of times. So the equivalent EMF ideally should be 20 volts. That is what you should get. Is that right? You should ideally get 20 volts. But do you think you will get 20 volts reality? Do you think you will get 20 volts reality, my dear warriors? No, right? Correct. Because some of them are wrongly connected. So now, because some of them are wrongly connected, think of it this way. There are only how many? 7 cells which are connected in the proper manner. And there are 3 cells which are connected in the wrong manner. There are 3 cells which are connected in the wrong way. So what will happen? Resistance wise, there is no change. Whether you connect it that way or this way, it doesn't matter. So it should be still the same. So RS will be 4 plus 4 plus 4, 10 number of times, no change in that. It will still be 40 ohms only. So equivalent internal resistance is still 40 ohms. There is no change in that. But for EMF, definitely there will be a change. So ES will be, there are 7 such cells, each of 2 volts. So 2 multiplied by 7 minus 3 cells of 2 volts each. That's it. 7 twos are 14 minus 6 guys. This will be basically 8 volts. So instead of 20, what you are getting now is 8 volts. What you are getting now is basically 8 volts. Massive difference just because 3 cells will now nullify 3 cells here. So out of 7, 3 went off. Only 4 effective cells are remaining. Each cell will be 2 volts. So 4 into 2 is 8. That's another way of looking at it. Yeah. Cool. Shall we go ahead, my dear warriors? Understood till this point? Awesome. Let's see some questions coming up on your screen. Calculate the charge on each capacitor as shown in the figure. As you can see over here, both the capacitors are basically in series, no doubt. So because they are in series, we can say the net capacitance in series will be C1, C2 divided by C1 plus C2. There are only 2 capacitors. So 10 into 20 divided by 10 plus 20. So it will be 200 divided by 30, which is 20 by 3 microfarad. That is your equivalent capacitance. Charge is capacitance into voltage. Capacitance is 20 by 3 micro into voltage is basically 30 volts. 30 and 3 cancels, 10 will be remaining. 10 into 20 will be 200. So 200 microcoulomb should be the answer, right? Each of them will be having 200 microcoulomb. Cool, everyone? Now I know the question over here did not mention voltages, but if by chance the question was find the voltage across 10, find the voltage across 20. Example, what will you do? Voltage is basically Q by C. What is the charge? The charge on each of them is 200 and capacitance is basically 10. This is microcoulomb. This is also micro cancels. 0, 0 cancels. So it will be 20 volts. This will be basically 20 volts. If you similarly talk about the voltage across 20 microfarad, it will be charge, which is the same, which is 200 micro upon capacitance, which is basically 20 microfarad. So this will just make it 10 volts. So that's how you can find out the voltages also across each of the capacitors. Cool. So moving on to the next question. Find the equivalent capacitance of the combination shown over here. Well, first things first, as you can see that this capacitor and this capacitor, both of them are basically in parallel. And in parallel, what you do is basically add the capacitances, right? They are capacitors. So 10 plus 20, that's it. So 10 plus 20, that's basically 30 microfarad. Now that 30 microfarad is nothing but in series with another 30 microfarad. These both are basically in series. So in series, what do? Use the parallel resistor formula. So C equivalent will be C1 C2 C1 into C2 divided by C1 plus C2. Correct? So how much will it come out to be? It will come out to be 15 microfarad. Right? Everybody with me? Just check it out. 15 microfarad is the correct answer. Very good. Good evening, Pravina. Yes, Dharnishwaran. Yes, Arborine. Yes, very good. Awesomeness. Moving ahead to the next question on your screen. Find the equivalent resistance of the following circuit. This is HC Verma question. Well, again, I can see that these two resistors are basically in parallel. Now they are resistors. Now when they are in parallel, what you do is R1, R2, R1, R2 divided by, remember they are not capacitors. If it was capacitors, I would have added them. Resistors have to use the reciprocal formula. So that will be 300 divided by 40, 0 cancels. So that should be 15 by 2, which is 7.5 ohms. Now that 7.5 ohms is basically in series with that remaining resistance of 2.5 ohms. So as a whole, which is in series, the equivalent resistance should be just 7.5 plus 2.5, which is nothing but 10 ohms. Yes, the correct answer is 10 ohms. That's how you find out the equivalent resistance. Great. Right? Very straightforward questions. We are just leveling up slowly. Moving on to the next question on your screen. Here it is. Figure shows a part of the electric circuit. The potentials ABC are marked current through the 20 ohm resistance. Guys, now this is the question where you use again my potential method. Remember using Kirchhoff's laws with the potential method. Sivan, how about this? Why don't you put up the doubt after the session is over in the comments, and definitely I'll help you out with it. Okay. So here is what I will do. I'll just assume, maybe I'll need some more slides over here. Just create a duplicate. I'll just assume the voltage over here to be X. This point's voltage, how much is it? A is nothing but 30, B is nothing but 12, and C is nothing but 2. Okay. Let us take the currents also. The current will go like this. Let's say I1. It will come out like this. Let's say I2, and it will come over here. Let's say it is I3. So using current law, Kirchhoff's current law, I1 will be equal to I2 plus I3. What is current 1? Current is voltage by resistance. Voltage is basically 30 minus X, high minus low. Current goes from high to low, divided by the resistance. Current number 2, high to low. Current will go from high to low. So it will be X minus 12 divided by the resistance, plus current number 3, high minus low. High is X minus 2 divided by the resistance, which is 30. 0, 0, 0 cancels. 0, 0, 0 cancels. Okay, so therefore I'll get 30 30 minus X is equal to X minus 12 by 2 plus X minus 2 by 3. You can also take LCM if you want, which is basically 6. So it will be 3 times of X minus 12 plus 2 times of X minus 2. This 6 can be further multiplied over here with 30 minus X. 30 minus X. So just do that. So 6 into 30 minus 6X is equal to 3X minus 12. 3 is a 36 plus 2X minus 4. Solve this and tell me what is the value of X that you are getting. Solve this and tell me what is the value of X you are getting quickly in the chat box. Come on, my dear warriors. Yep. Let me know what is the value of X that you are getting. Want to see whether you're active or not. X is 20, says Adiksha. Very good. Okay, it has to be more than 2, more than 12, but less than 30. So the only, yeah, values which will fit in will be more than 12 and less than 30. Okay, once I get that, you have to find what is it? Current through the 20 ohm resistance. So I2 will be voltage, which is X minus 12 divided by the resistance. X is just, we found out as 20 minus 12 by 20, which is 8 divided by 20, right? Which is nothing but 4 divided by 10, which is basically 0.4 amperes. Yes, 0.4 amperes. Yes, that is the correct answer. Very nice. We found it out. 0.4 amperes. We didn't have to use much space. So this was asked in J 2023. So multi-step problem, usage of method of potentials along with Kirchhoff's laws and Ohm's law. Cool? Very straightforward. Very nice question. Moving on to the next question. A wire of some resistance is bent to form a circle. Find the resistance between the two diametrically opposite points. Very interesting. Now the entire wire's resistance is 10 ohms. Mind it. So this entire wire, right, from A, D, C, B to A, D, C, B, and back to A, that entire wire is basically 10 ohms. Now look at this. You have to find between two diametrically opposite points. Just imagine I take one part here and the other part. Just take this part over here. This will be exactly half the wire. That whole wire is 10 ohms. So this is half the wire. So this will be basically how much? 5 ohms. And the upper part will also be 5 ohms. So is it not like saying you are having a resistance of 5 ohms over here, and you also have another resistance of basically 5 ohms over here? Both of them are basically in parallel. So what is the equivalent resistance? R1, R2 divided by R1 plus R2. So that is nothing but 25 divided by 10, which is 2.5 ohms. So 2.5 ohms should be the answer, which is correct. A lot of people I've seen writing the answer as 5 ohms. They think that it is half the wire. So they write it as half, which is 5. That is not correct. It is 2.5 because they have become in parallel. Yes. What an interesting question, guys. Moving to the next one on your screen. A wire of some resistance is cut into n equal parts. These parts are connected in parallel. The equivalent resistance of the combination will be how much? Okay, let's try to think. Imagine you have a long wire of resistance R ohm. You break it down into n equal parts. Imagine like this. N parts. Each part will contribute in some resistance so that the total resistance would have been R. So 100% each part will be R by N, R by N, R by N, like that, R by N. Because I know if I add them together, what I will get is my original resistance back. So each resistance is R by N, 100%. Now you take each of them, but now you have connected them in parallel. You have basically connected them in parallel, something like this. Okay, you have connected them in parallel. Each of these R by N resistances. So what will happen to the equivalent resistance? So 1 by Rp will be 1 by R by N plus 1 by R by N, like that, N number of times, because there are N such resistances, they are in parallel. So this will be, take N on the top, so this will become N by R, but it is N times, so into N. So it will become N square by R is 1 by Rp. So how much will Rp be equal to? Take the reciprocal, so it will be R divided by N square. R divided by N square, which is option number D for IIT Delhi. How many of you wrote D for IIT Delhi? Come on, guys, keep answering. Don't just sit quietly. Yep. Be proactive, be alert, keep solving, keep a rough book, keep a rough sheet, keep solving, even if you're watching it live or recorded. And yeah, as you're doing that, do not forget, many people get engrossed in the lecture, sir, I'm enjoying the lecture. You forget to express your gratitude by liking the video. So do that right away, right now. Yes, do that right away, right now. Smash the like button in case you have forgotten. Moving on to the next question on your screen. In the circuit diagram as shown in the figure below, the current flowing through the resistance of 3 ohm is x by 3 ampere. The value of x is how much? Current flowing through 3 ohm resistance is how much? Okay, so I can see that there are two batteries over here. Can I not convert it as one single battery? I think so. Just look at this two. Oops. Just look at these two. What are they? There are two batteries in series. So 8 volts here, 4 volts here. It will be totally 8 minus 4. That is the net EMF, which will be 4 volts. 8 this side, 4 this side. So 4 will be remaining. And internal resistance wise, how much will it be? R1 plus R2. So 0.5 plus 1, which is basically 3 by 2 ohms or 1.5 amperes. Okay. 3 by 2 ohms or 1.5, sorry, ohms. Now, if you look below over here, all these things, 3 and 6 are basically in parallel. So because they are in parallel, how much will that EMF, equivalent be? 3 into 6 divided by 3 plus 6, 6 3 is 18 by 9 is 2 ohms. 2 ohms and 4.5 ohms. Yes, they are together in series. They are together in series. So it will be 4.5 plus 2, which is basically 6.5 ohms, which is basically 6.5 ohms. So this whole circuit now boils down to a simple circuit now. A battery, a battery of basically 4 volts and internal resistance 1.5 ohms and connected to an equivalent resistance below, of how many ohms? Basically 6.5 ohms. 6.5 ohms. So what will be the current flowing in this circuit, my dear warriors? What will be the current flowing in the circuit? The total voltage by the total resistance. So the current is the total voltage by the total resistance. Total voltage is 4. Total resistance is 1.5 plus 6.5, which is 4 by 8, which is basically 0.5 amperes. Is it right? 0.5 amperes. But that is not the question. But that is not the question. The question is something else. The question is something else. The question is, how much current is flowing through 3 ohm resistance? How much current is flowing through the 3 ohm resistance? So here is what we can do over here. Forget this part. I got the current is 0.5 amperes. I know this current of 0.5 amperes will get divided over here. I know it will definitely get divided over here. Is that right? How will it get divided? How do I know how much will it get divided? I know one thing. It is that the voltage across both of them is same. So that voltage, if I write it over here, this is I1, this is let's say I2. I can say it is I1 into resistance, which is also I2 into that resistance, which is basically 6. I into R is the voltage, correct? So how about this now? I2, take I1 below, by I1, I2 by I1 will be 3 by 6. Is that right? Which is basically 1 by 2. So I2 by I1 is basically 1 by 2. Use componendo. So I2 plus I1 divided by I1 will be 1 plus 2 divided by 2. I2 plus I1. What is I2 plus I1? I2 plus I1 is basically that current which is there over here, which is 0.5 amperes by I1. 1 plus 2 is 3 divided by 2. So naturally, what do I get? I1 as, take 2 on the top. So 0.5 into 2 divided by 3, which is nothing but 1 by 3 amperes. So current number 1 is 1 by 3 amperes. So the value of X is the number 1. The value of X is the number 1, which is the correct answer. That is what we got. Yes. Yes, anime god, you are quite late, but you can join in. It's not like you should not understand much. If you have some basic knowledge, you will be able to catch up at this point. Okay. Fair enough, guys. So what did we do? We have used many concepts here. Equivalent battery concept, equivalent resistance concept, converting the circuit into a simple circuit to find out the current. Then lastly, we use parallel resistor concept. to find the current in each branch, because I know the voltage will be the same, but currents will be different. Loved it, everyone? Yep, very nice. Very nice. Moving on to the next question on your screen. Here it is. Look at this question, my dear warriors. Okay. There are four cells of 2 volts joined in parallel, providing a current, providing a current to a external circuit of 215 ohm resistance joined in parallel. The terminal voltage is 1.6. Calculate the internal resistance. Okay, let's draw the circuit diagram to understand it better. Only then we will proceed. There are 4 cells of 2 volts each. Okay, 4 cells with some internal resistance. This is 2 volts internal resistance, and the thing is, these are the cells which are in parallel, and, they are providing current to an external circuit. Okay, let's take this as our external circuit, and this external circuit itself has 2 resistors in parallel. What are those 2 resistors which are in parallel? That is 15 ohms. This is 15 ohms, and this is also 15 ohms. That is what it is connected. The voltmeter reading, yep, okay. So that means the voltage across these 2 points is measured to be 1.6 volts. That is what this means. So this is the explanation of this passage, which has no diagram, which can happen in JEE. You might get it pure words, so you'll have to draw and only then proceed. Without that, it will be very confusing. Syed Sheikh, yes, you are late. Guys, tell me if we are starting the classes early, or what do you want me to start only very late? But then we also have 9 o'clock, PYQ classes. And I'm seeing that you guys are not attending too many PYQ classes. I was seeing the views, I was seeing your attendance and likes. Tell me if you don't want the PYQ classes, then we'll stop it. And yeah, I want to see more attendance in the road series. So yeah, the older videos, yes, you have been watching, but the newer videos, the older videos, which we conducted in June, May, and whatever, probably July start, maybe you have been watching, but the last 2-3 weeks, I've been seeing that you guys have been distracted or not motivated or not attending for whatever reason. I want to see that attendance come back, guys. Yeah. Good evening, Mr. Pradeep. Yeah. So now what do we do in this particular question? Well, these 2 resistors basically are in parallel. So I can treat them like one single resistance of how many ohms? 7.5 ohms. Then that is one part of it. That is basically one part of it. Next part, each of these resistances are R, 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 R. So the effective resistance in parallel, think about it, 1 by Rp will be 1 by R, but 4 times. So therefore, it just means Rp will be R by 4. So the equivalent internal resistance over here will be R by 4. What about the EMF? That will be just E, because each of them is the same voltage. So parallel, all the voltages will be the same only. So it will just be 2 volts. It will just be 2 volts. I hope that is very, very clear. Now, this is clearly mentioned that this is 1.6 volts. So think about it. 2 volts is over here. This is 1.6. How much voltage will be there across this resistor? How much voltage will be there across this resistor? Think about it, guys. Across that particular resistor. Yep. From here to here, the change of the voltage potential difference is 2. Out of that, 1.6 is here. So the remaining, so the potential difference across internal resistance, how much will it be? It will be 2 minus this 1.6, which is basically 0.4 volts, which is basically 0.4 volts. If you talk about the current in the circuit, we can easily find it out using Ohm's law. The current in the circuit is voltage divided by the resistance. Voltage is 1.6. Resistance is basically 7.5. Resistance is basically 7.5. So you can might as well write it as 16 by 75. Now the last thing, if you just consider this part of the circuit, just the internal resistance, because the same current will flow using again Ohm's law, using the Ohm's law again, using voltage is nothing but current multiplied by resistance. Only for this part, the voltage drop here is nothing but 0.4. The current is nothing but 16 by 25, and the resistance is nothing but R divided by 4. R divided by 4. So you can see that we can definitely cancel this 4 with this 16. This 4 goes with this 4. You will have 0.1 over here. Yep. This was 75. I wrote that 75 is 25. These are called as silly mistakes. So this is not 25. This is 75. Yep. So 75 into 0.1 is 7.5. So R is basically 7.5 ohms. Perfect. Yep. These are silly mistakes which do happen at times. Great. Cool. So now let's go to the different forms in which we can connect resistors and capacitor. First thing is called as a disguised form. So what is this disguised form? Basically, it will be a complex looking circuit, but at the end of the day, it will be a simple series or parallel combination. Sometimes it happens that it looks like it is neither series nor parallel, but when you rearrange it, you will get it. So how do you go from here to here? There are multiple approaches to go from here to here. One way is to either visualize, but this can be uh, very, very tricky. The second best way is mark the potentials, and then decide what is happening. See, if the current is getting current splits, and voltage is same, then 100% it is in parallel. But the same current, one after other, it flows, then it is in series. Usually this is easier. Visualization depends from person to person. Somebody might find it easy, somebody might find it difficult. That's all I would say. Okay? So I'll just explain you with a simple solved example maybe. This is one of the most famous examples. Imagine a resistor here, and another resistor here. This is R1, this is R2, and this is, let's say, R3. And what happens is somebody takes a wire and connects it here, somebody takes another wire and connects it here, and the question is find the equivalent resistance. Now, at the start, it looks like, okay, it's a weird looking circuit. What could it be, sir? Maybe the current directly goes here like this, because you see this big wire connecting two ends, and you are easily tempted to think that all the current goes like this. But don't be fooled into thinking like that. The current can also go like this. Also, imagine the current could also go probably like this. Oh, sorry, what is it? Maybe it can also go like this. Okay, so it's not that current only chooses one path. Current will go via many paths. Somewhere it will be more, somewhere it will be less. So it is not right to think that, oh, current will only go like this. That is wrong. Rather, mark the voltages. See, let's say I mark this point as A. This is also A. The same wire is connected here. This will be also A. If I mark this point as B, even this point will be B. The same wire goes here. This will be also B. Now just think about it. If from A versus from B, if I start, what happens is A's connected to R1, A is also connected to R2, A is also connected to R3, B is also connected to R3, R2 as well as R1. And for R1, R2 and R3, the voltage difference is VA minus VB, VA minus VB, VA minus VB. What did I say? If the voltages are the same and the current is splitting, which it is, in fact, in this question, the current is splitting in different ways. So it must be in parallel. Whether you want to visualize it or not, that's a different story. But it is in parallel because the voltages are VA minus VB. So this is R1, R2, R3. That's it. So a complex looking circuit has been simplified into a series parallel circuit. This is what disguised method is. Is that absolutely clear? Everyone with me? Yes. Awesome. So that is why 1 by RAB will be just 1 by R1 plus 1 by R2 plus 1 by R3. Awesome. Perfect. Let's look at the question. This is there in Tatva module. Look at this. So many capacitors are there. And you have been what's the effective capacitance between points P and Q. Let me tell you, this is disguised form. Yes, it is disguised form. It's just that you have to see the disguise. In this particular problem, there are few things which are very obvious. Let me tell you what. Check this out. Here, oops, this point and this point have the same voltage. So all the current can completely bypass from here. There is no need for it to go here because complete current can be bypassed here. So what is the use of these capacitors? Nothing. In fact, these two capacitors are said to be shorted. Short means you take 2 points and connect it with a wire. That is called as shorting. Shorting means connecting 2 points with the same potential, same wire. So these are useless, which means I can redraw this particular diagram to be this one. There is no use of this. There is no use of this. Now over here, you can see one interesting thing. If this point has potential P, even this point has potential P, that is Q. Let's say I call this point as R. This wire is also R, same wire. If this is R, even this is R. Now, what we can do is from this particular point P, I can say it is connected to this, it is connected to this, it is connected to this. R is over here. This is basically your R. And between R and Q, there is one more basically, I can say capacitor. So now between R and Q, we have one capacitor, C. And between PR, there are three capacitors, same voltages. So 100% they are again in parallel. They are just in parallel, guys. That's what you can see over here. C, C, and C. These three, because they are in parallel, hence the capacitance will be C plus C plus C, which is basically 3C. This 3C and C, they both are in series. This 3C along with this C, they both are in series. And in series, the combination works like this: C1 C2 upon C1 plus C2. So it will be 3C divided by 4. That is the answer. 3C divided by 4. Good evening, Siva. Understood, my dear warriors? Pakka, shall we go ahead to the next one? Pakka, shall we go ahead to the next one? Let me know. Yep. Show some energy, show some fire in the chat box. Yep. Very nice. How about this one? Find the equivalent capacitance between points A and B. Find the equivalent capacitance between points A and B. Very simple, guys. Let's see if you can figure this out. Between points A and B, you have to find out the equivalent capacitance. What do we do? Again, see if you can figure out some capacitors, are they together? I think they are. Observe this. These two capacitors actually are in series. So in series, C1, C2 by C1 plus C2, which means it is 0.5 microfarad. Now, if you redraw it, if you basically forget this, and this will now become 2 micro, sorry, not 2, this will become 0.5 microfarad, right? I've replaced these two with one single capacitor of 0.5 microfarad. Don't you see that this point has the same voltage as this point? If this is X, this is also X. If this is Y, this is also Y. So 100% they both are in parallel. 100% they both are in parallel. So in parallel, what happens? In parallel, the equivalent capacitance adds. So 0.5 plus 1, which means it is 1.5 microfarad. Okay. So then what I can do is, I don't need so many capacitors also now. Yeah. So all of this together is 1.5 microfarad. So this is basically now 1.5 microfarad. Don't you see this 1.5 and 1? They both are in series now. Are you able to see that? Are you able to see that, my dear warriors? Yes, this 1.5 and 1, they both are basically in series. Yes, they both are basically in series. So what will happen now? Again, use C1, C2 by C1 plus C2. So 3 by 2 multiplied by 1 divided by 3 by 2 plus 1. So it will be nothing but 3 by 2 by 5 by 2. 2 cancels. So it will become 3 by 5 microfarad. This and this 1 microfarad, they both are in parallel. This along with this, they both are in parallel. So in parallel, you just add the capacitances. So 3 by 5 plus 1, which is nothing but 8 by 5 microfarad. 8 by 5 microfarad. Yep. Is that clear? Now, awesome, Ritvik Krishna. You got sent in your school, college exams, I guess. Awesome. God bless you. Yep. Very good. Short deck, you got, oh, it's your birthday. Oh my God. Nice. Many, many happy returns of the day. Short deck, and hopefully next year you'll be celebrating your birthday in some nice IIT, in some nice college with a lot of cool friends, a lot of new people from all over the country. God bless you, my dear kid. Okay, great. Sai Harshik Kola, sir, why are you so serious? Oh my God. No, bacha. The thing is, the topics we have to cover a lot, and plus exam is there around the corner. It's not that I'm serious or anything. It's just that I'm in the flow, in the mood. That's all. Nothing like that. But yeah, we will have some casual and fun sessions as well, which will be motivational as well as, you know, a little bit relaxing. Probably will take off some burden off your head. Don't worry about it. Okay, let's go. Infinite form is what we are going to do next. See, there are infinite resistors or capacitors, and I want to find the equivalent capacitance or resistance. You might think, sir, infinite resistance, I mean, resistance will also be infinity, no, sir. No, like you have studied sequence and series, sum till infinity, and all of that. So, does not mean just because there are infinite things, their sum will also be infinity. So, it's something like that only. So, usually you might have a series kind of question, that series like GP. Okay, or sometimes you might have GP, or I would say converging series, converging series. Sometimes you might have a repeating pattern. Repeating pattern. So let's see both these kind of questions. If it's a series question where it is GP or converging, directly use our formula which you have learnt in maths, a formula of sequence and series, whatever you have learnt. And if it is a repeating pattern formula, whatever that pattern is there, okay, you separate it out, you identify that pattern and assume pattern you identify, whatever it is, and assume the equivalent resistance or that equivalent capacitance as X and try to redraw the diagram. Redraw the diagram and you will see most likely it will be either in series or in parallel. I'll explain you all of this with the example. I'll explain you. Okay, don't worry. Let's take this particular example over here. Find the resistance of the infinite network right over here. Now, do you see a repeating pattern? Do you see a repeating pattern? Yep. Everyone, you can see what is the repeating pattern? 2 3 2 3 2 3 2 3. Correct? Everybody is able to see. Okay. So this is basically this kind of question where the pattern is getting repeated. So you identified the pattern. Equivalent resistance or capacitance, assume it as X and redraw the series parallel circuit. So the equivalent resistance between these 2 points, let me assume it as X. Now think about it. Forget the first part. Just imagine the remaining right between these 2 points. Right between these 2 points. Okay. Right from here, this 2 and then this 3 over here. And this continues. This 2 and this 3 over here. This 2 over here like this. Okay. It continues. It continues till infinity. Isn't this diagram the same as this diagram? You will be like, sir, this is 1 less than infinity. But do not forget, infinity minus 1 is also infinity. Infinity plus 1 is also infinity. So strictly speaking, this particular diagram is also going to have the same resistance X only. Is going to have the same resistance X only. Do you guys agree with this statement or not? Everybody give me a thumbs up in the chat box right away right now. Yes, very good. So can I then say that our diagram actually is, this is that repeating part, this is that repeating part. So just take that first part, which is 2 ohms. Then you also have 3 ohms right over here. And this whole thing is having collectively X ohms. This whole thing collectively has how much ohms? It has basically X ohms. Now, doesn't it look like a normal series parallel problem? Definitely it does. Everybody is able to see that it does look like a series parallel problem. 3 and X are in parallel. So combine both of them. They are basically in parallel. So the parallel combination will be R1 R2 divided by R1 plus R2. That is in series with 2 ohm. That is in series with 2 ohm. And what I get again between these 2 points is X ohm. So the equivalent circuit is the series combination of 2 ohms and this one, which is basically 2 plus 3x divided by 3 plus x, and the equivalent is also x. That is what I see. The equivalent of these two, which are in series, will be R1 plus R2. R2 is 3x by 3 plus x. And this whole thing is also x only. Wow. So just have to play with this now. So guys, what will happen? Multiply by 3 plus x on both sides. So x into 3 plus x is equal to 2 into 3 plus x plus 3x over here. So this will become 3x plus x square is equal to 6 plus 2x plus 3x. 3x cancels, 2x comes on the other side. So x square minus 2x minus 6 is equal to 0. This is the quadratic equation which I am getting, which means I will be definitely getting two roots, So x is equal to minus b, means minus of minus 2, which will become plus 2, plus minus root of b square, which is 4, minus 4 into a, which is 1, c, which is minus 6, so it will become plus 6 over here, whole thing divided by 2 into 1, so plus or minus, 6 fours are 24, 24 plus 4, 28, so it will become root of 28, whole thing divided by 2, which is 2 plus minus 28 is 7 into 4, root of 4 is 2, so 2 root of 7, whole thing divided by 2, 2 cancels, so it will become 1 plus minus root 7, but obviously we cannot choose the negative sign because then the resistance will become negative, so the actual value that I will choose will be the positive one. So the actual value of x will be 1 plus root of 7 ohms, which should be the correct answer. Yes, 1 plus root 7 is the answer. So in these type of questions, usually this is what happens. You will identify the repeating pattern. You take one of that part. The remaining part is also infinity series only. So assume that as x because the original one was x. So replace that whole thing with x, redraw it as a simple series parallel circuit to get the equivalent itself back to x. Solve it, usually you will get a quadratic equation. Is that right? Clear? Shall we go ahead? Okay. Next type of question. Find the equivalent capacitance. You can see there are again infinite number of capacitors. There are many branches in this. First has one capacitor, then it has two, then it has four, then 8, then 16. It's basically powers of 2. And each one will have different number of capacitors in it. See guys, whenever you have capacitors in parallel, what happens? Assuming all the capacitors are same. So if n capacitors, sorry, not parallel, in series. If n capacitors are in series, what happens? CS, 1 by CS, you will go by 1 by CS. You will go by 1 by CS. So 1 by CS will be 1 by C plus 1 by C, like that n number of times. So it will be basically n by C. Therefore, CS will be C divided by n. That means this particular problem will convert into the first capacitor or the first branch has only one capacitance, C. The next one has two capacitors in series. So if it has two capacitors in series, the capacitance will be C by 2. So in the next branch, I will have the capacitance as C by 2. Okay. In the next branch, there are how many capacitors? Just check this out. 4 capacitors. So it will be C by 4. In the next branch, there were 8 capacitors. So it will be C by 8. And this will continue, of course. Now, all these capacitors are in different branches. They are in parallel. So because they are in parallel, what I should do to find the equivalent capacitance, I should just add them because they are in parallel. All these are in parallel. So just add them. So it will be C plus C by 2 plus C by 4 plus C by 8, so on and so forth. And this will have infinite number of terms. This looks to me like a GP series, like a geometric progression. Is that right? And what is the sum till infinity? A upon 1 minus R. A is first term upon 1 minus common ratio, which is half. So 1 minus 1 by 2. So hence it will be C by 1 by 2. So 2 will go on the top. So hence it will become 2 times of C. So the equivalent capacitance is basically 2C. Equivalent capacitance is basically 2C. Got it? How to solve this question? Yes. Ishida, I want to thank you a lot. I got my seat in ISER. I can't explain the journey I had with you for the past 2 years. Thanks, sir. Thanks for being a teacher, friend, and a mentor. Thanks a lot. Ishida, my goodness, you got in ISER. Which ISER? I'm really, really happy that you guys are coming back. That shows your loyalty, that shows your gratitude, and that shows your humbleness. Be like this only throughout your life, and may you achieve everything, guys, in ISER. ISER is a very, 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 very amazing, amazing research institute. You'll have lots and lots and lots of fun, lots of opportunities too. I really hope that maybe you guys come down sometime to Bangalore. We should actually meet, and you should actually come on the screen and talk to the kids out here. It will be really amazing. Yep. Okay. UCID exam, definitely, Sarthik, you should write it if you are interested in design. uh, I think the forms roughly come in October, November. Deadlines are also during that time, so definitely you should write it. It's a very good examination, very good colleges too. Okay. Right. So let's go to the next type of problems where you have plate questions. Plate questions. Now this is specific to capacitors only. Okay, not anything else. This was done. Okay. So in this type of question, what happens is, say for example, you will be given plate arrangements, maybe something like this. And maybe there will be 1 point here, 1 point here, and they will be asked, find the equivalent capacitance. What you need to do? Very straightforward. Each plate will have two surfaces, and a capacitor is made of two plates with two surfaces facing each other with opposite charges. Correct? Each capacitor is nothing but two plates with two surfaces internally facing each other. So just try to identify the capacitors. See, there are some faces which are not even facing anything. What is this side facing? Because each plate will have two sides, one on the top, one below. What is this doing? Nothing. So this is not doing anything. Even this is not doing anything because it is not facing anything. It is facing the sky, the atmosphere. Nothing, no use. The only ones which are actually facing something is this face number 1, face number 2, face number 3, and face number 4. 1 is facing 2, 3 is facing 4. Remember, this plate over here is from the side view. It has two sides, 2 and 3. Each of them are basically like plates. Think of it like this. Some of you might have some difficulty in visualizing. So these are basically plate problems, something like this. This is basically B, and this is what is exactly done over here. This is A. This is the same thing. These two are the same thing. Okay. So obviously you can see this part is completely useless. The part below is also useless. So there will be a capacitor between these two plates, and there will be also a capacitor between these two plates. That is what will happen. Is that right? That is what it means. So now what is the capacitors that we have? We have C12. We also have C34. Think of it like that. I will name it like that. C12 and C34. C12, one is connected to A. Okay, so I can then write it as A is basically connected to A is basically connected to 1. A is also connected to 4. A is not just connected to 1, it is also connected to 4. I hope you can see that. A is also connected to the number 4. So I'll just show it like that. I'll just show it like that. Now opposite plate or surface 1, I have the surface number 2. So I'll put the number 2 here. Opposite 4, I have the surface number 3 over here. Oh, perfect. 2 and 3 together are connected to B. 2 and 3, basically, what are they connected to? They are connected to nothing but B. Oh, now I know these two are basically in parallel. These two are basically in parallel. So what will happen, guys? What will happen? So this problem into this problem into this. So they are in parallel. That's it. So just add the values. Just add the values. So the capacitance between A and B will be C plus C, which is 2C. So it will be 2 times epsilon naught A divided by D. If area is given, distance is given between the plates, 2 times epsilon naught A divided by D. Yes. Cool. Sayarshik, glad I cleared your doubt. Ishida, I got into Aizhar, Tirupati. Wow. And Trivandrum and Mohali, I choose Tirupati. Nice. Very good. Very good. Awesome. Tirupati is good. Okay. Okay. Shall we do now questions based out of this? So what is the logic? First, identify the surfaces which are useless. Then identify the surfaces facing each other. 1, 2, 3, 4, 5, 6, 7, 8. Start connecting these surfaces to those endpoints. You will get a circuit. And then from that circuit, either it is series or parallel, solve it and you'll get the answer. Let's see some questions. See, this is the question that we have. Let's try to solve it. First of all, there will be useless surfaces. Like the uppermost surface is useless. The lowermost surface is also useless. Also, you will notice that this is surface 1, this is surface 2, this is surface 3, this is surface 4, this is surface 5, this is surface 6. Okay, so let's see what does it come out to be. A is basically, A is a point right over here, and let's say B is a point right over here. Let's see what is A exactly connected to. A is connected to 1, A is also connected to 4 and 5. A is basically connected to 1, 4 and 5. So A is connected to 1, 4 as well as 5. Opposite 1 we have 2. Opposite 4 we have 3. Opposite 5 we have 6. Where are they connected? 6, 3 and 2. 2, 3 and 6. Do you see 2, 3 and 6? They are all connected to point B. Oh, perfect. So 2, 3 and 6, they are all interconnected to point B. Now I can see what is exactly happening. They are all in parallel. They are basically in parallel. Hence, basically, the equivalent capacitance between A and B will be C plus C plus C, which is 3C, which is 3 times epsilon naught A divided by D. That is the answer. Very, very straightforward. Yeah. I hope this is very, very clear. Sayarshik, now is not the right time where you decide whether you want to do BTech or whether you want to do design. Right now is the time where you give all the exams. Depending on what score you get, then you decide. A lot of people think that I will choose this and then I will see, I will, I want to do this particular course only. I'm confused. Don't do that. That is worst mistake. First, prepare everything. You don't know what rank you will get. You don't know what scores you might get. So always better to be, prepared for every situation. Okay. So prepare for BTech, prepare for BR, prepare for B design, whatever. Whatever we get, we'll see accordingly. Now is not the time. Okay. How about this particular question? Find the equivalent capacitance between A and B. Again, there are some useless things. Surfaces like this one and this one, completely useless. Useful ones, 1, 2, 3, 4, K, 5 and 6. Let's see what happens now. Guys, there is one thing though. Between 3 and 4, do you notice both of them are connected to point B only? Both of them are connected to point B exactly. So 3 and 4 ideally should not make a capacitor. Think like this. If I tell you this is plate number 3, this is plate number 4, and I tell you, listen, both of them are connected to the same point B. Both of them are connected to the same point. It's basically shorting it. It's basically shorting that capacitor. So it becomes completely useless. It becomes completely useless. So ignore this capacitance. So basically between 3 and 4 also you ignore. So the only two capacitors will be C12 and C56. So let's see what happens. Point A somewhere, and here it is point B. A is connected directly to 1 as well as 6. is connected to 1 as well as 6, is connected to 1 as well as 6. Opposite 6 we have 5 and opposite 1 we have 2. 2 and 5 both are connected to B. 2 and 5 both are connected to B. So they both are definitely now in parallel. They both are definitely now in parallel. That's it. Hence our answer will be CAB will be C plus C, which is basically 2C, which is 2 times epsilon naught A divided by D. 2 times epsilon naught A divided by D. Is that clear, everyone? Very good. Let's go to the next question coming up on your screen. Oops, here it is. This is a JEE 2024 question. There is a big plate. In front of it, there are three one-third plates separated at different distances. Question is find the equivalent capacitance. Now, again, the useless surfaces are this, this, and this. In fact, you will see that there will be one capacitance here. There will be also one capacitance here, and there will be one capacitance here. I hope you can see that. This one I can call it C1. This one I can call it C2. This one I can call it C3. These plates are connected to each other via this metal. These plates are the same thing. Why not look at it as if there is C1, there is C2, and C3, three capacitors. All these upper plates, all these lower plates are connected together. You can see that this is connected to point A. All these plates are basically connected to point B. They are basically in parallel. Can you see that? Can you see that, my dear students? They are basically connected in parallel. That's all. So if they are connected in parallel, let's see the equivalent capacitance. The equivalent capacitance between A and B will be C1 plus C2 plus C3. What is C1? C1 is epsilon naught area divided by D. What is C2? Epsilon naught area divided by the distance will be 2D. C3 will be this. So epsilon naught A by 3 and this will be 3D. So it will become epsilon naught A divided by 3D, and then you will have 1 plus 1 by 2 plus 1 by 3. What will this become? Think about it. LCM is basically 6. So it will become 6 plus 3 plus 2. So equivalent capacitance between A and B will become epsilon naught A divided by 3D multiplied by whatever is there in that bracket. What is there in that bracket? 6 plus 3, 9. 9 plus 2 is 11. So it will become 11 by 6. It will become 11 by 6. 6 threes are 18. So it will become 11 epsilon naught A divided by 18 times of D. That is the equivalent capacitance between A and B. That is the answer. Yes. Option D. What a brilliant question. Three capacitors were there side by side in parallel. Yep, very good, Siva. Kumar, very good, Dharneshwaran. Yes, Arburain. Very good. Excellent. Keep it up. Moving to the next type of questions where you will have some kind of symmetry involved in the problems. Now, when I say symmetry, there could be different kinds of symmetry. The kind of symmetry that we are looking at is as follows. You will have some circuit. I'm not saying what kind, but you might have some kind of circuit. All these are resistors, example, and you have to find equivalent resistance between 2 points. what you should do is, in these kind of questions, first of all, join the points between which you want to find the equivalent resistance. These are the 2 points where line joining the points between which equivalent has to be found, where you want to find the equivalent between them. Next, drop a perpendicular bisector. What will you do? Drop a perpendicular bisector. This is that next line. What is this? This is your perpendicular bisector. And check for symmetry. Whatever is there on the left is there on the right. So yes, symmetry. So symmetry basically exists. The moment the symmetry exists, what happens is, in the next step, whatever comes on that line of symmetry, remove it. Whatever comes on the line of symmetry, basically remove it. So you can basically ignore this part. You can completely ignore this particular part and then redraw, and then basically redraw the entire circuit. Sometimes what happens, you will notice that on the line of symmetry, you might sometimes get some resistor, capacitor, etc. if it is like this, or sometimes you might just get a junction, either like this or like this. Okay, you might get a junction, or sometimes you might get some kind of a device or a wire. You might get device or basically a wire. If you get a device or a wire on that line of symmetry, on that perpendicular bisector, then it is actually very simple. Then you just forget that device, and just redraw it like this. So you basically disconnect. You have basically disconnected it. You disconnect it. If it is like this, that's when the trouble happens. In such a scenario, what you do is basically extend it, pull it up in this manner, pull it up in this manner, pull it up, stretch that wire, you stretch it along that line. Yes, stretch it like a wire, stretch it like a wire. And once you get this, this diagram is same as this diagram. So you go back over here, do whatever you did. Basically, you can remove this part and you will see disconnected two branches. Okay, I will explain this to you with an example, but I'm showing the procedure. Not many people tell you this. So I'll repeat what I said. Whenever there are problems involving symmetry, you find those 2 points where you want to find the equivalent, drop a perpendicular bisector, you see whatever is there, top, bottom, left, right is the same. Then see what is there on that line of symmetry. Is it a junction or is it a device or a wire? If it is a device or a wire, directly remove it. If it is not, if it is a junction, then stretch that junction to become a wire. Once it becomes a wire, it looks like this. Now you can remove this part, disconnect it, you will get two separate things. That's what you need to do. Is that point clear? Shall we do an example? Let's do. In fact, I think I should have kept an example here. Okay. Look at this question. Do you see any line of symmetry? Yes or no? Quickly think and tell me. Do you see a line of symmetry? Yes, I think so. This is the line joining points A and B. You can see that this is, oops, there is a definitely a line of symmetry. On that line of symmetry, whatever is there on the left, on the right is the same thing. So whatever device is there can be completely ignored. So this particular device can be ignored, completely ignore it, forget about it. And then I can redraw the circuit because I have ignored that particular part. If I ignore that particular part, what will happen? This is how it will look. This is how it will look. Now it looks very simple, isn't it? Now it looks very simple. Now we can solve it easily. How? These two capacitors are in series. So when capacitors are in series, what is the equivalent capacitance? C by 2. These two capacitors are also in series. So also C by 2. This one is C. Now these three are in parallel. I hope you can see that. So you have C by 2. You also have another C by 2. And you have a C. All these three are in parallel. I hope you saw that. So once they are in parallel, you just have to add them up. You just have to add them up. So equivalent capacitance between A and B will be C plus C by 2 plus C by 2. C by 2 plus C by 2 is C. C plus C is 2C. Hence the answer is 2C. Is that right, everyone? Got it? Starting from here, you drew the line of symmetry and you saw that there is some device, resistor, battery, whatever. Ignore it. Completely ignore it. So now once you ignore it, that's it. It looks like a simple series and parallel circuit. Very, very straightforward. Okay, let's go to the next question coming up on your screen. Here it is. Do I have a line of symmetry? I think so. Let's figure it out. We do have a line of symmetry right over here. We do have a line of symmetry. And I can't break this capacitor, but I can see very clearly that at this particular point, I have a junction. I have a junction. And whenever I see a junction, what do? I split that junction up into two parts. I split that junction up into two parts. So here is what I will do. I will just probably redraw it like this. I'll just redraw it like this. I've stretched it now. I've stretched it now. Okay, I've elongated that junction. So first I identified there is a line of symmetry and there is a junction. I stretch it. And once I stretch it, what do? I see that this part is on that line of symmetry. Ignore it. Ignore that particular part. So let's draw the ignored diagram and see how does it look. Looks something like this. Yes, this is how it will look like. See this? Starting by line of symmetry, junction, stretch it, ignore that part, and it looks like this. Now it is a simple circuit. Now it is a simple circuit, right? So let's see what does it come out to be. These two capacitors are basically in series, right? So it will be C by 2 because they are in series. And this C by 2 and this C is in parallel with each other. So this in combination with this, because they are in parallel, so it will be C plus C by 2, which is 3C by 2. That is in series with these two. Check this out again. You have C, you have 3C by 2, and you have C again. And these two are also in series. So it will be also C by 2 again. So you will have C by 2 over here. This is A, this is B. On the top, because they are all in series one after the other, we'll have to use the series formula. So 1 by CS is 1 by C plus 1 by 3C by 2 plus 1 by C. LCM is basically 3C. So it will be 3 plus 2 plus 3, which is basically 3 plus 3 is 6 plus 2 is 8, 8 by 3C. So CS will be 3C divided by 8. So this whole combination is 3C divided by 8, which is in parallel with C by 2, which is in parallel with C by 2. So CAB, which is parallel combination, you just will add 3C by 8 3C by 8 to this C by 2. So it will become 3C. LCM is basically 8 plus 4C, which is basically 7C divided by 8. 7C divided by 8. Very good, Siva Kumari. Awesome. Proud of all of you. Got it? Everyone, how to do these questions? Basically, this is the explanation of this trick which I have written it down over here. Whenever you see a junction, stretch it. Once you stretch it, remove that device or that wire and disconnect it. Okay, that is the trick. So I have shown you a problem where you actually have a device on the line of symmetry, you ignore it and solve it like a simple series problem, parallel problem. Or when you have a junction, okay, no issues, you stretch it, ignore it, redraw it with series parallel and solve it. There was one more question which was asked in JEE 2024. I think we will be able to easily solve this particular question. I think there is a quick line of symmetry which you can easily see over here in this particular problem. So definitely we can ignore many things like this one as well as this one, this as well as this. So this problem looks much more simpler actually without them. It's very simple without it. These two are in series, so 2R. They are resistors. So in series, again 2R. These two also in series, again 2R. 2R, 2R, 2R are in parallel with each other. So this whole combination which you see, this whole combination which you see, which is in parallel, that will be 2R divided by 3. There are 3 resistors, so 2R divided by 3, resistor becomes small. This 2R by 3 is in series with R and R. Check this out. You will have R over here, you will have 2R by 3 over here, and then again you will have R. So add them up to find the equivalent resistance. So it will be R plus 2R by 3 plus your R. Correct, everyone? So R plus R is basically 2R. So plus 2R by 3. 2R common. 1 plus 1 by 3 is basically 4 by 3. So it will become 8R divided by 3. 8R divided by 3 is option number A. Perfect. So you can see again, we saw that there is a line of symmetry. Whatever device is there, we can ignore it and then redraw it as a simple series and parallel circuit. What a question, right? Okay. Now, a much more better version of this, hopefully now we have come, Wheatstone's bridge. A better version of this is the Wheatstone's bridge, where even if there is no line of symmetry, but there is a ratio which is there, then also you can remove certain parts or certain wires or certain devices. That is exactly Wheatstone's arrangement, where you have multiple branches, but the resistors or the capacitors are in a ratio, so you can ignore whatever is there in between. Let me show you an example. There's some battery. That battery is supplying some current. It is going through this branch as well as this branch. Correct? Now, there is a resistor here, another resistor here. In this branch, a resistor here, another resistor here. If this resistor and this are in a ratio, whatever is connected in between them, voltmeter, ammeter, galvanometer, battery, resistor, blah, 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 nothing doesn't matter. The device or that wire will be useless if the ratio is the same, which means P by Q should be equal to R by S, then the device in between is completely useless. This arrangement is called Wheatstone, but when this condition is satisfied, then this is said to be a balanced Wheatstone. Then it is said to be a balanced Wheatstone. Now, this is not just for resistors, is also valid for capacitor. Also valid for capacitors. It's also valid for capacitors. So if it was C1, C2, C3, C4, C1 by C2 is C3 by C4, whatever is in between becomes useless. So it becomes useless. These two are in series, these two are in series, and their combination is in parallel. In fact, I can extend it to even more. Just imagine, just imagine there is something over here. Okay, there is some device here, 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 here, and then there is also wire connecting like this, wire connecting like this. There could be even more devices here. Let's say I can call this device C1, C2, C3, C4, C5, C6, C7, C8, C9. It could be resistors, it could be capacitors, doesn't matter. If this is called as extended Wheatstone, if C1 is to C2 is to C3, the one in this branch is equal to, example, C4 is to C5 is to C6, which is basically in the middle branch. And same thing over here, C7 is to C8 is to C9. If these ratios are equal, na, then whatever is there in between can be completely ignored. This, this, all these things can be ignored. All these things can be ignored. And what happens is your entire circuit will become a very simple one. That's it. You'll just have these ones here, these ones here. Now you can see they are in simple series and parallel. That's all. You can completely ignore whatever those lines are there connecting them. So it will now become a simple series and parallel combination. Simple series and parallel combination. Okay, this is very, very interesting trick, which is called as the Wheatstone's method for balancing. And this is only valid if they are in the same ratio. Whether there are two resistors, two capacitors, 3, 4, 100, doesn't matter. The ratio in every branch should be the same. That's all. This is the Wheatstone's method. Let's solve some questions based out of this. This is in H.C. Verma. Find the value of resistance so that there is no current in this. Now, when they say that there is no current in 50 ohms, what does it mean? Hari, maybe you'll have to watch the lecture from beginning, no issues. If there is no current here, this means it is completely useless. And now, I think you are able to also identify that there is a branch here and there is another branch here. It looks like a Wheatstone. So, if it is useless, that means it should be a balanced Wheatstone. It should be a balanced Wheatstone. Is that right? It should be a balanced Wheatstone. And when will it be balanced? When this and this are in the same ratio, which means 10 divided by 20 should be R divided by 40. 0, 0 cancels. So R will be 40 divided by 2, which means it should be 20 ohms. That is what it means. So answer is 20. 1 is to 2, 1 is to 2. That should be the ratio. Is that okay, everyone? Understood the logic behind it? Very nice. Let's see another question coming up on your screen. This was asked in JEE 2023. There is a network of resistors, and the question is, what is the equivalent resistance between A and B? I don't know if you saw this, but I can identify a Wheatstone right over here. Let me in fact highlight it for you. Let me in fact highlight it for you. Check this. And in that, this is useless. This is useless. Can you see that? This is useless. 1 is to 1, 1 is to 1. So that's it. So this is useless. So the top two are basically in series. So you will get 8 ohm over there. These two are also in series. So you will again get 8 ohm over there. And in between over here, you have 16 ohms. That's it. This is B and this is A. So this is the actual circuit. So this circuit has been converted into this circuit. This is useless because 1:1, 1:1. It's a Wheatstone's arrangement. Wow, done. That's it. So what will be my last step? They are all in parallel, right? They are all in parallel. So 1 by RAB, which is in parallel, will be 1 by 8 plus 1 by 8 plus 1 by 16. 1 by 8 plus 1 by 8 is 2 by 8, which is 1 by 4 actually. So it will become 1 by 4 plus 1 by 16. LCM is 16. So 4 goes and 1. So it will be 5 by 16. So equivalent resistance will be 16 by 5 ohms. 16 by 5, which is basically 3.2. Yes, perfect. 16 by 5 is 3.2. Yes, Arborine. Yes, Dharneshwaran. That is the correct answer. Very good. Proud of all of you. Very nice. By the way, I had also seen one question where, they have given this. This was a very good question. Let's see if you can solve this. You have to find the equivalent resistance between A and B. This is given to be R. Say this is 2R, this is 3R, this is 4R, this is 8R, something like this. These are the resistances given. Now, whenever this kind of question comes, right, people think that this is nothing but, sir, this is parallel circuit. Well, it was parallel as long as this was not a resistor and this was not a resistor. It was just a direct wire. That was the disguised form. Here also it is disguised, but it is disguised even in better way. Actually, this is a Wheatstone bridge. Correct me if I'm wrong. See if you can visualize this. I'll just rewrite it. I'll just rewrite it like this. From point A, I am getting R and 4R. I'm getting R and 4R. Okay. And this R is connected here. This 4R is connected here. Between these 2 points, you have 3R. So you have basically 3R right over here. That is what I got till this point. Okay, fine till this. R and 4 are connected to point A. R and 4 are connected to point A. Eventually, they are connected between 3R. Now, this 3R is connected via 8R and 2R to point B. Is connected via 8R and 2R to this particular point B. Does this not look like a Wheatstone's bridge now? Yes, definitely. So we can completely ignore this. We can completely ignore this. And if we ignore this, now we know what is there on the top. They are basically in series. So from our point A, we have these two resistors in series, which is 12R. These two in series, which is basically 3R. And their combination is basically in parallel. So the final answer to this particular question, RAB will be this into this. So 12 into 3 divided by 12 plus 3 into R. Is that okay, everyone? So that is the equivalent resistance between A and B. So how much will it be? 12 3 is a 36 divided by 15R. That is the answer. RAB is 36 by 15R. Yes. 12R by 5. Yeah, you can divide it by 3. No issues. Divided by 3. So that will be 12R divided by 5. Correct. In the simple fraction. So these questions are disguised forms of Wheatstone's bridge, which is this one. This is the disguised form of your Wheatstone's bridge. Very, very interesting concept. So let's go now to the next type of questions where you will see Dielectrics involved. Dielectrics are involved. Ready for it? So we are doing all varieties of questions. After this, you will never ever face any issues. Any question comes in JEE exam, you are prepared for it. So what type of questions are these? Let's have a look. Sometimes you will be given that there is a dielectric slab or slabs placed either fully or partially. We know one thing though, if there is a capacitor and you completely fill it with completely fill it with a dielectric medium, then the new capacitance is basically K times of C. If it is completely filled, if it is completely filled. But the moment it is not completely filled, that's when the problem happens. That's when the problem happens. So let's see if there is a formula for that. So there is a formula. In fact, let me explain this to you. Usually, when you have area A, distance D, and dielectric constant K, okay, what is the capacitance? You write it as epsilon naught K A divided by D, right? Epsilon naught Ka divided by D. Just put that K below. So it will become epsilon naught A divided by D by K. That is the capacitance that you usually write, assuming it is completely filled with the dielectric. Assuming it is completely filled with the dielectric. Now, imagine there is K1 here, then K2 here, air, whatever. For air, what is the dielectric constant? It is 1. Each of them filled for thickness T1, or let's say I call it D1, D2, D3, Dn. These are all basically the individual thickness of those slabs or that medium which is present inside. There are different slabs here, different mediums which are present over here. What to do in that case? Then the equivalent capacitance is given as follows. Use this formula only, very simple, but write it slightly differently. Epsilon naught A will come on the top, but instead of D by K, here it will be summation D by K. That means it will be D1 by K1 plus D2 by K2, like that till Dn by K. That's it. That's the only difference. Instead of D by K, you put it as summation D by K. That's all. Straight forward, guys. Yep. Very nice. So that is the formula. Epsilon T by thickness by K, distance by K. Whether it is air, whether it is not air, doesn't matter. Okay? It doesn't matter. If it is air, K value will be 1. Let me show you some special cases on that, where you will have capacitors one after the other, or like this, or even like this. See, if it is like this, there are two options for you. First option is use the formula directly. Use the formula which I directly gave you. C is epsilon naught A divided by sigma D by K. The second option which you have is treat it like series problem. Usually you would not do that unless you have a lot of time in the exam. You can call this as C1, C2, C3, Cn, like that. And you can treat it like there are different capacitors one after the other in series. That is another way of doing it. But usually avoid this unless it is needed, or maybe it becomes simple for some reason. Okay. This is the first case. Second case is when they are side by side like this. Please understand, now you cannot use our formula because these are the terminals. There is a slab on the top and below. So the charges are going to get distributed like this. So in such a scenario, you have no other option but to treat them like parallel capacitors. Treat them like parallel capacitors. There is no other option, guys. No other option. This is one terminal, this is another terminal, this is K1, this is K2. So treat them like parallel capacitors. Treat them like parallel capacitors. Okay, till this point, is it clear? So if you see that your charge is crossing one slab, then other slab, then other slab, it has to cross one slab, then it is in series. If it is like this, then it is in parallel. As simple as that. There can be a combination also like this. These two here, this one here. What will you do if this is your terminal? If you have a combination like this, all you need to do is, it's a combination of series and parallel. Think of it in a manner this way. There is one capacitor C1 here. After that, you have another capacitor C2 over here. Okay. And then below, you have another capacitor C3 over here. You have another capacitor C3 here. So these two are in series, one after the other. Their combination is in parallel with another capacitor of capacitance C3. Is that clear, everyone, with me? Great. Perfect. So again, you can have this special case too, where you have the slab here and then these two things over here. So all these are different cases, guys. All these are different cases. Again, you can see these two are in parallel and they are after this K1. So you can just think of it as if there is a capacitor 1 and then the charge gets separated into two different capacitors over here. This is C2 and this is C3, which themselves are in parallel like this. So this is how this will be. I hope all these special cases are clear in your head. Everyone, let me know quickly in the chat box. Are all these special cases clear in your head? If it is series, then it is simple, or you can directly use the formula. If it is like this, it is in parallel, side by side. Now, if it is a combination, it could be two series and then parallel, or parallel first and then in series. So depends from case to case. Sir, can I crack NIT if I start the preparation from now, sir? Can I crack it? Definitely. Mehboob Farooq, if you start from now, yes. If you keep asking that question, then no. So you have to start. You have to pick it up. You cannot say, sir, today it's 8:30 now. It's okay, sir. I will start from tomorrow. If you say I will start from tomorrow, then no. If you start right now, then yes. If you make the arrangements, keep your study table clear, or make a room or whatever, make your own space, make a schedule, stick it on the wall, your ambition, your goal. If you start watching the lectures, if you download whatever, you have enrolled in a proper course, you have started your preparation, or you make your strict schedule, 100% you will be able to do it. You plan accordingly what you need to do in this month, that month, you will be able to do it. All right. Now we'll also come to charge and energy flow problems. I hope you remember the energy stored in a capacitor and all those things. Like the energy stored in a capacitor is half CV square. We have done this. I'm just doing a quick revision, or a half Q square by C, or basically half QV. Whereas if you talk about the power loss in a resistor, it will be basically I squared R, or V squared by R, or basically voltage into current. Also, you should know the power which is supplied by a cell is EMF into the current. Just like voltage into current, a battery does not cause any loss. It gives the energy into the circuit. So it is E into I, as simple as that. These are the fundamental formulas of energy which you will need for energy loss, charge flow, etc. problems. So you will see questions where a switch is closed, switch is turned, this happens, that happens, how much loss, how much gain, how much charge flows, etc. etc. One of the most important questions which I feel is this one, where Look at this. You have simple capacitor. There is a battery, could have some internal resistance. That's it. Okay. And you analyze this simple problem where this capacitor is charged by a cell. A capacitor is charged by a cell. Now, one more thing before we go ahead. This is power supplied. Power is energy per unit time. So, if you talk about the energy which is supplied, by a cell, it is EMF into the charge which flows. Okay, this is for a battery. Whatever I have written over here is for a resistor with some current in it. And whatever I have written over here is for a capacitor. Okay, three different things. Energy is charge into EMF because current into time will be charge because power is energy by time. So take that time here, time into current will be charge. These are the formulas. Okay, I will need it for solving this question. Okay, say for example, I ask you in this particular question, this battery is charging this capacitor. What is the energy stored in the capacitor? Okay, so the energy stored in the capacitor is given by the formula half capacitance into voltage. Voltage is basically E, so half CE square. Isn't that right? Half CE square. Perfect. Awesome. Now, if I ask you, what is the energy which is supplied by the battery? What is the energy which is supplied by the battery? Let's try to find that out. So, energy supplied by the battery. It will be, as mentioned here, EMF into the charge which flows. EMF into the charge which flows. How much charge flows through the battery? It is the same charge which is stored on the capacitor. How much charge is stored on that capacitor? That charge which is stored on the capacitor is capacitance into voltage. So it is basically C into E. Hence it will be CE square. Now you should think carefully. Battery gave CE square, but capacitor stored half CE square. It's like your mom and dad, when you're going to school, they give you pocket money, 100 rupees. But you use that 100 rupees to buy some stationery, not worth 100 rupees, only 50 rupees. So where did you spend that remaining 50 rupees? Obviously on something else. You chilled out. You ate some snack, you partied or whatever. You bought something else, right? So supplied C square, but you're storing half C square. Where did the remaining go? Obviously, the remaining energy is lost as heat. Remaining is lost as heat in the wire or the internal resistance. The wire or the internal resistance. So how much will that be? It will be nothing but CE square minus half C square. So that will be half C square. So half the energy is just lost as heat. Half the energy is just lost as heat. That is the interesting part. In fact, always you will see this equation holding true where you will notice that the energy which is supplied by the cell will go into two things. Number one, in changing the energy of the capacitor, and the remaining will be going as the loss. This is a very, very important equation. This is a very important equation. Whatever the battery supplies, which is C square, will go in increasing the energy, half C square, and the remaining half C square is going as the loss. Very important equation. Is it absolutely clear? Everybody with me? Okay. You can use it for many questions. So let's solve some questions based out of this. So we have seen the charge flow and the energy standard formulas. This was already done. This you already know from 10th standard also. This is something additional which you have learned today. Power supplied by the battery is voltage into current, so EMF into current. But energy wise, it is EMF into charge because current into time is charge. This I have already given to you in the lecture 1 of capacitor. Okay, cool. Let's solve some questions. I think I already showed the answer for this. Okay, so I've showed the answer. Just take it up as homework. We'll be doing more questions. I'll be doing more questions. Okay, so yeah, just do it later on. Take it as homework. Okay, because I've showed the answer. I'll show some unsolved questions. That will be better. Find the amount of charge which flows through the switch after closing it. Okay, let's try to solve this question, my dear students. Let's try to solve this question. Okay, how much charge will flow after closing this particular switch? Now, what to do in such questions is think, write, calculate everything before and after. So before closing, what will happen? Before closing, just look at this. So before closing, what you will see is, you will see two capacitors basically in series connected to that particular battery. That's all. So because they are in series, the equivalent capacitance will be C by 2. So the charge on each capacitor is basically the same because they are in series. So it will be nothing but CV. C is C by 2 into voltage. CV by 2 is the charge on each of them. Everybody fine till this point? Okay. And because this is positive terminal, this will be positive, this will be negative, this will be positive, this will be negative. What happens afterwards? Let's have a look. What happens afterwards? Well, you will have this capacitance. These two will be in parallel. Do not forget it. So this will be C, this will be 2C, and this battery will be just connected over here. Okay. So C and 2C, they are in series. So the series combination will be C1 C2 by C1 plus C2. So it will be 2C divided by 3. The charge on both will be the same. The charge on each is going to be the same. So it will be 2C by 3 into the voltage. 2C by 3 into the voltage. Okay. What? Be careful. This 2C by 3 won't be on this or this. It is the total charge on both the capacitors. 2C by 3, 2CV by 3 will be here, will be also here. But this 2C is the equivalent of these two. Do not forget that. So actually, on the top capacitor, what will you see? On the top capacitor, what will you see, guys? This is that switch which was closed. Yep. You will see half the charge will be on the top, half the charge will be here. So you'll see minus CV by 3 here, plus CV by 3 here, plus CV by 3 here, minus CV by 3 over here. This is what you will see exactly. This is what you will see exactly after closing the switch. Before closing the switch, the top capacitor did not even have charge. There was no charge here. There was no charge here because this was not connected. Now, when you connect the switch, if CV by 3 has come on this plate from no charge, how much charge has gone through the switch? Think about it. Earlier, there was zero charge. Now, I am saying there is minus CV by 3 charge. That means what? From the switch, how much charge has flown? From the switch, how much charge has flown? CV by 3 has flown through this particular switch. Is that clear? Yep. Awesomeness. That is the correct answer. Let's find out. Yes, it is CV by 3. Very good. Congratulations. Awesome. Moving on to the next question. Find the amount of charge flown through the switch after closing this. Again, a different variety of question. Okay. Again, do before and after, guys. That's all you need to do. So before, what will happen? These two capacitors will be in series. These two capacitors will be in series, plus, minus, right? Connected to this particular battery. So because they are in series, their equivalent will be C by 2, and charge is going to be the same. And how much will it be? C into V. Afterwards, when you connect it, all the charge will bypass it. This will become completely useless. So after you close it, it's just one single capacitor. You have shorted the other capacitor. Okay, that's it. As simple as that. So the charge is just C into V. Just C into V. As simple as that. So if you look at that capacitor before and afterwards, okay. Which one? This capacitor, let's look at. Before, on this plate, the negative one, the charge was minus, how much was it? Minus CV by 2 on this plate. I'm talking about this particular plate. Afterwards, on this particular plate, how much charge is there? It is minus CV. Oh, from minus CV by 2, it has become more negative, minus CV. So, where would it go? Where would that charge go? Okay. Or there is one more thing over here. Even this had before plus CV by 2 plus CV by 2. Later on, that has no charge at all. That has no charge at all. We have to look at both the things. We have to look at both the things. Yes. So, my dear warriors, yes, so plus CV by 2 is here, minus CV by 2 is over here. Okay. So basically, what would have happened? This charge became 0. That means plus CV by 2 went like this. Think about it. At that junction, here is what I will see. CV by 2 became 0. That means it disappeared. So CV by 2 went like this. Minus CV by 2 became minus CV. It became more negative. That means CV by 2 charge would have gone out of this plate. Where will these two charges go? It will have to go over here. CV by 2 plus CV by 2 will just become CV. CV by 2 plus CV by 2 will just become how much? CV. Is that clear, my dear warriors? Is that understood? Pakka? Yes, very nice, very nice. So I have taken this junction to understand it. I saw that these are the charge distributions before. This is the charge distribution later on. In the later on one, I say that because this is shorted, there is no charge on it. So at this junction, if I analyze it properly, I will notice that CV by 2 became 0. So CV by 2 has disappeared. Minus has become more negative. So that means the positive charge has gone away from it. So CV by 2 has gone here. They will combine and it will become CV. As simple as that. Very good. Awesome. So these are the kind of questions, guys, that we will see. Okay. Again, find the heat which is developed in the circuit after closing the switch. Okay. Guys, now this is C and 2C. Okay. Earlier, I think this was C and C. So now this is C and 2C. Okay. So if you look at it before, it was C here, 2C here, this was the battery. So C equivalent will be C into 2C because they are in series upon C plus 2C, which will be 2C divided by 3. So the initial energy which will be stored will be half capacitance into V square, which is 2 cancels, which will become CV square by 3. That is your initial energy, which is stored in the total capacitors. When you close the switch afterwards, then what happens? That capacitor becomes completely useless. You just have one capacitor because the other one is just shorted. That's all. So the equivalent capacitance will just become C, and the final energy stored will be just half C V square. That is the final energy stored. Now, I have seen a lot of people doing this. What they do is, sir, this is final, this is initial. Final minus initial is the heat generated. That is completely wrong. Do not do that because some charge will also go through the battery. And if you do not calculate that, that will be a big mistake. What is the charge over here? The charge which is stored finally will be just C into V. What is the charge which will be stored here? What is the charge which is stored here? Capacitance into voltage. So 2CV divided by 3. So think about it. 2/3 became 1. That means the charge has increased. So how much charge actually has flown through the battery? How much charge will actually flow through the battery? Because earlier it was 2/3, now it has become 1. So the charge which flows through the battery will be CV minus 2/3 CV, which is nothing but how much? CV divided by 3. CV divided by 3. Awesome. Now, if that is the scenario, I can also find how much work was done by the battery. And that is always into EMF into the charge which flows. What is the EMF? V. What is the charge which flows? CV by 3. Hence, it will be CV square divided by 3. And now we know the equation. The work done by the battery is nothing but the change of the energy in the capacitor plus the loss which you encounter. So the work done by the battery is CV square by 3. Correct? What is the change in the energy of the capacitor? Final minus initial. So it will be half CV square minus CV square by 3 minus CV square by 3 is going to be added to give you the loss. So half minus 1/3, 3 minus 2 is 1. So 1/6 CV square. So this will go over here. So it will become CV square divided by 6. And this will be CV square divided by 3. And this will be equal to our loss. So finally, how much will our loss be equal to? 1/3 minus 1/6. 1/3 minus 1/6, 2 minus 1 is 1. So it will be CV square divided by 6. It will be how much? CV square divided by 6. Is that clear, everyone? Yes, CV square by 6. Correct. Perfect. So this is how you solve these questions. These are amazing, 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 amazing questions, guys. I hope you are loving it altogether. Cool. Now, there are some more variety of questions which I want you to tackle with. These are the last type where a charge capacitor connected to uncharged, charge connected to another charge capacitor and energy transfer. Okay, all these kind of questions. Very, very simple technique I will teach you to solve these questions where a capacitor is connected to another capacitors and you have to find energy, charge, voltage, etc. Okay, a parallel plate capacitance is charged, energy stored is E1. Now connected to another in parallel, energy stored is E2. Find the ratio. Okay. Draw the diagram. Simple. This is before. What is it? 2 farads connected to a potential V. Connected to a potential V. Energy stored is E1. So how much will be E1 using the formula? Half CV square. It will be half into capacitance is 2 into V square. So it will be basically V square. So that is E1. Now the capacitor is connected to another identical in parallel combination. See, this capacitor would have stored some charge. The charge which is stored on it will be CV. C is 2, so it will be 2V. Now, when you take this capacitor which has a charge, which has basically a charge of 2 times of V, and you place it near uncharged identical capacitor, and now you are going to connect it, what will happen? You will see that the charge will get distributed, and because both of them are going to be in parallel, this is going to be a parallel combination. So I can treat it like one single capacitance of how much? 2 plus 2, which is basically 4 farads. And this charge will stay there only. It will just redistribute. That's okay. But the total charge will be remaining same. So you will see the charge is conserved and that will still be equal to 2 times of V. So the final energy stored, which is going to be E2, will be half charge square by C. So what is the charge? Charge is basically 2V. So it will be 2V whole square by C equivalent, which is basically 4. So this will become 4, 4 will cancel. So it will become basically V square divided by 2. V square divided by 2. So our E2 is basically V square by 2 and our E1 is basically V square. So this ratio of E2 by E1 will be basically 1:2. So that should be the answer, which is option number A. Yes, that is correct. Perfect. Thank you, Sushmita. I'll definitely take care of my health. It's like I'm not recovered only from my throat infection. Yep. Very good. Awesome. Moving on to the next question on your screen. This was in JEE 2022. A capacitor of 5 is charged to 30. Okay. This is charged to 30 volts using a battery. Battery is then removed. Charged capacitor is connected to another capacitor of different value. Earlier it was identical. Now it is different. When the switch is closed, the charge flows. Equilibrium or the capacitor charged to is how much? Okay. Fair enough. See, before, if you talk on that 5 microfarad capacitor, this is positive, this is negative, the charge initially will be CV. Capacitance is 5 micro, voltage is how much? 30. So 3 5s are 15. So 150 microcoulomb is the original charge on the capacitor. Now, when you connect both of them, actually they are side by side, they are in parallel. So this and this, actually you can convert it into a single capacitor like this because they are in parallel, and the capacitance of this 5 microfarad and how much is it, 10 microfarad, will make it 15 microfarad. This is positive, negative. Charge has to be same. Charge is the same. How much is the charge, guys? So the charge has to be still 150 microcoulomb. This charge will be same, but it is the charge on the total capacitance. Remember that. So, if you talk about the voltage, if you talk about the voltage across both the capacitors, that voltage will be charged by the capacitance. Charge is 150 micro. Capacitance equivalent is 15. So the voltage 15 microfarad. So it will just become 10 volts. 10 volts is the voltage across these capacitances. voltage across these capacitances. So if I'm interested in charge on 1 or 2, in this case I'm interested in charge on 2. So the charge on the capacitance 2 will be capacitance into voltage. Capacitance is 10 micro, voltage is basically 10 volts. So it will become 100 micro coulomb. If it was on the first one, then it will be 5 micro into 10, which will make it 50 microcoulomb. If you add both of them, 100 plus 50, you will still get 150 microcoulomb. So on the second one, it is 100. That is the answer. On the first one, if it was asked, it will be 50 microcoulomb. Very simple. TS, you have a lot of Hindi channels. This is an English medium channel because a lot of students who prefer learning in English, and the English that I'm speaking is very laddu, simple English, Indian English. It is not British English, American English, right? It is very simple English because there are a lot of students who love to learn from us, right? Perfect. Let's go to the next question coming up on your screen. This is a JEE advanced question, level 3 question. Look at this. This is asked in 2011. There is a switch which is aligned here. You move it to 2. Question is the percentage of its energy stored which is dissipated after the switch is turned to position number 2. Very nice question. Okay, let's try to do this. Let's try to do this. I'll take 2 scenarios over here. First scenario, the switch is in this particular position. In this particular position, voltage V, capacitance 2 microfarad. So this one is completely useless. This one is completely useless. Just concentrate your attention only on this part. Just concentrate your focus and attention only on this particular part of the circuit. So the charge which is there initially will be CV. So it will be 2 micro into V. That is one thing. If I need it, initial energy will be half CV square. Capacitance is 2 micro into V square. So it will be V square micro, whatever joules. That is one thing. This will be positive. This will be negative. Next scenario. When you move it to this side, then this will become completely useless. Okay, this part will become completely useless. Just focus your attention only on this much part of the circuit. Now, what you will notice is this 8 and 2 are basically in parallel. So 2 microfarad is basically parallel to 8 microfarad. So the equivalent combination will become 10 microfarad because they are in parallel, right? They are in parallel. Do not forget that. And the charge of how much charge was there? 2 micro, 2 micro into V is conserved, on it, So maybe I can find the final energy stored, which is half charge square by capacitance. So it will be half. Charge is nothing but 2 micro V square divided by equivalent capacitance is 10 microfarad. Okay. So 2 square by 2, 2 will remain. Micro square, V square by 10 micro. So micro cancels. So it will become V square divided by 5 and micro over here. So micro V square by 5 is the final energy. So there is some loss now. There is 100% some loss of energy which is there, which is involved. So because the stored energy gets dissipated, how much is lost? How much is the loss? Because battery is not doing work, this is final, this is initial. So loss will be final minus initial, which is magnitude. Just take the magnitude of it. So it will be micro V square by 5 minus this thing over here, which is micro V square. How much is that loss? It is basically 4 by 5 micro V square. That is the loss of that energy. That is that loss of energy. The question is, how much percentage of it stored got lost? So the percentage loss is how much ever is that loss upon how much ever was stored, and then you multiply it by 100. That's it. So how much is that loss? We just figured it out. It was 4 by 5 micro V square. How much was there initially? Initially, it was micro V square. It was nothing but micro V square. And then you multiply it by 100. Micro V square cancels. 4/5 of 100 is basically 80%. So answer is 80%, which is D. Yes, that is the correct one. Perfect. What a brilliant question. Sushmita, the way I'm following your lectures, which made the concepts clear, thank you for that. Sushmita, yes, you can follow JEE classes, but these kind of questions are very uh, less probable. I mean, negligible, I would say, which will be asked in NEET. But yeah, for concept clearance, this is like the best thing. But okay to watch the class, but when you practice, don't practice JEE advanced questions. Please practice NEET questions only. Okay, because speed, number of questions, attempt, pattern, everything is different. You should be used to that circumstance. Concept wise, it's fine. I mean, there is no issue with that. In fact, it will be deeper only, whatever I do over here. Cool. What a nice question, guys. I mean, I really loved this question. This was a level 3 question. So we started with the initial part where we forgot this part because it was connected here. We found out initial energies and charges. Then we took this part when the switch was moved, and then we saw that these two are in parallel. So equivalent capacitance, final energy. So if found how much energy differed, that would be going as loss. So if you divide the loss with the original energy and multiply by 100, you will get the percentage of the energy which gets dissipated. What a brilliant one. So this is a question which is there for homework. I'm pretty sure you will be able to crack it. Answer is there on the next slide. The PDF will be shared on the Telegram channel. Okay, so make sure you're joining the Telegram channel. The link is there in the description box. Let me show that to you right over here. Okay, so you can see Telegram sessions. All the PDFs will be uploaded here. Plus, there is also Jungle Book, which we have kept so that you are finding it difficult to see any of the classes. It's there right over here. Physics, chemistry, maths, the YouTube class, the subject, the PDF note, the DPPs, everything right over here. Okay, that's your Jungle Book. Also keep this in mind that we have a proper test series which is scheduled for all the JEE aspirants, which is completely year long, which includes mains and advanced. So please check that out. The link is there here. And don't think, sir, I'll wait for my portions to be over. No, already thousands of students have started their journey with this test series. You will learn a lot. Plus, it will be a good collection of questions. There are more than 60 tests, 64 tests actually, mains plus advanced, which are freshly made for all of you for this particular year. And it's a very affordable price point, 1,499 rupees. You can see all the other details of the test series below over here in the FAQs. Okay, the link is there in the description box. It's a complete test series for mains and advanced till next year May, especially for droppers and 12th standard students. Okay, so use that. So we are done with current, electricity and capacitors for now. Next, I'll be starting off with magnetic effects of current, magnetic sources. So stay tuned on the channel. Also Newton's laws from 11th standard point of view. Okay, take care. Bye bye. Have a great time. Make sure you're liking and comment below that yes sir, current and capacitors is done and dusted. Current and capacitors is done and dusted. Want to see all your comments in the comment section. Bye bye. Take care. Have a great time. Hasta la vista.